The delay? Okay, we're gonna go in now. And yeah, sorry for the delay. Technical issues, plus I'm still making slides. I'll make a few more in the break. Yeah, can you? I can do it in the break. I didn't do it yet because I was still adding stuff right to the last minute. Okay. So assignment 2 is going to be released soon, whenever I have fully verified everything. So it'll be due basically 3 weeks from when I release it. So I'm hoping to release it tomorrow or Thursday. I'm going to talk a little bit about what it is. You're going to optimize two-dimensional convolution on FPGAs. It's going to be a bit like assignment 1. You'll use the same tools. It's a somewhat more complicated computation where there's a little more room for how you organize it. Prize for the highest throughput, fame, right? It's going to be announced to the group here, so that's obviously the key reason to do it. Also an Amazon gift card, probably not going to make up for your tuition, so probably not a really good reason to do it, right? There are probably easier ways to get an Amazon gift card. So the main thing you're going to do is see how do you optimize this on an FPGA. We're also going to use this as an exercise in how do you do rigorous comparisons. So you're going to compare to a CPU and GPU implementation. I don't want to have to teach you, and you don't want to have to learn in this course how to program a GPU as well and how to get the most. You probably know a lot about how to get quality out of a CPU, but we basically created high quality CPU and GPU implementations for you. So you just have to read them, say, yeah, you kind of understand what they're doing, and then you can compile them and run them in a few ways. So you just have to be able to give some high level explanation of how does this work, but you don't have to write it. You're going to run it and you're going to get a comparison. And you're going to compare the key metrics for this kind of computation: throughput per watt, and throughput per unit of area. I mean, people actually care about throughput per dollar, but per dollar is difficult because it gets into how much would these chips cost in volume and so on, which is usually hard to figure out. So a good proxy for that is just how big are they, because bigger costs more money. And the chips you're going to use, this will be in the handout, but basically they're the ones that I talked about last week. There's a reason I talked about what were in the UG machines is because that's what you can actually measure on, right? So I've given you the process technology and some of the key information about them, and the handout goes through that too. Okay, so this assignment's about convolution. So let's talk first about one-dimensional convolution. So convolution is a super important mathematical operation in all sorts of things, including signal processing. So one-dimensional convolution is actually very important. It's the basis of things like a finite impulse. Well, a finite impulse response filter is a one-dimensional convolution. Who's heard of a finite impulse response filter, like a FIR filter? Okay, so lots of people. So in signal processing, it's like a key building block. And this is this equation, which is just the equation for a one-dimensional convolution. You probably have to stare at that for a little while to make sure that the subscripts are all correct. But for example, if we want to do a low-pass filter, we can make a low-pass filter by taking a bunch of samples and multiplying them by our convolution or FIR coefficients. And you probably hopefully remember this from signal processing, right? So for a low-pass filter, your Fourier transform of what you would like in the frequency domain, you'd like something that just passes a certain band of frequencies. You want to see what do you need to do in the time domain. You need to convolve with the inverse Fourier transform of that, which is this sinc function, right? So you read off the coefficients from this function. This is continuous, but if we just read off at discrete points, the coefficients, that's what we would use in a one-dimensional convolution to approximate a low-pass filter. I'm not here to reteach you Fourier transforms, so if you're kind of going, I don't remember that course all that well, that's fine, right? This is just to motivate you that convolution is something that's used all over the place, and we want to be able to do it efficiently. Okay, so we're not going to do one-dimensional convolution, even though it's a super important operation, and you'll actually see in an FPGA that when we get into the DSP blocks, they actually have some structures to make them very good at one-dimensional convolution because signal processing and wireless processing is such an important market. We're going to do 2D convolution because it's a little more challenging, and that's used lots in images. It's used lots in images, and it's used in neural networks that work on images, okay? So a two-dimensional convolution, we're going to take images, and a convolution is you've got a window, so you've got filter coefficients, just like here I showed you filter coefficients that were one-dimensional, right? So you're going to multiply your delayed samples by different filter coefficients and add them up. In an image, our filter is two-dimensional. We're going to use 3x3 filters. okay? So 9 total pixels coming from a 3 by 3 region. We multiply every one of those pixels by our corresponding coefficient. We add them all up, we get one output. So for this output, this top left pixel in the output image, it's the convolution of this window with the input image. So it's the multiplication of 9 filter coefficients times 9 pixels, and you add them all up, and you get one output. In order to apply this, like notice that this input pixel, there's nothing around it. So to make it easier to apply a convolution without all sorts of special case logic, what you usually do is you pad the image. So you put a row and a column of zeros around it so that I can basically apply my convolutional filter at every single input pixel, and I basically never go to bounds, right? It just does the right thing. So that's a lot easier than trying to put a bunch of, in Verilog, this would be all sorts of like multiplexers and control logic to try to say, am I out of bounds and should I put in a 0? We don't want to do that, so we just pad the image so that you can apply the same filter everywhere, and if you're right at the edge, you just get a bunch of zeros added in, but way easier. Let's see, and you can compute, once I've got basically all of these pixels, so we're going to send you these pixels in order, and we will send them with the padding, okay? So you're going to get these pixels in order, and they're going to be streamed in row major order, okay? So that's what the text bench is going to do. So all this data is flowing into your hardware. You can't compute any outputs until you get this far. Once you get this many pixels, you can actually compute this output. Okay? Then every time you get a new pixel, you can compute a new output, right? Because you can just now keep shifting along. You can't compute this last pixel here until you get the very last pixel, which happens to be like a padding pixel for the image. Does that make sense? So you're going to output a little bit less than you get in as input. So your control logic is going to take that into consideration. And the lab tells you, how big the images are and so on, because otherwise this is not a solvable assignment. So you know how many columns there are, how many rows there are. Does that make sense? Okay. So what are you going to do? So I'm going to give you some starting hardware to get going with, and you're going to complete it and optimize it. So basically, the protocol by which you're sent data is very similar to what you had in assignment 1. So data inputs are marked as valid or not valid, right? So if iValid is high, then you actually have a valid input that cycle. You're getting 8-bit integer pixel data. So that's pretty common for images. So it's basically grayscale images. So you get 1 input pixel per cycle. If iValid is low, you didn't get anything that cycle, okay? You have to buffer up the input data. So in lab 1, you could basically, 1 input comes in, you could compute 1 output, right? You had everything you need. Well, now you can't compute 1 output just given 1 input. You got to buffer some stuff up so that you actually can form these windows where you can do convolution. So you got to have one part of this is properly buffering your input. You're going to have to compute all the required convolutions, and you're going to have to output them in the same order they came in. So row major order. So you go over the columns, then you go down 1 row. And you mark every output that is a valid pixel output as valid should be high. And your output is also an 8-bit integer. So a transformed 8-bit output. And you can only output, at most 1 pixel per cycle. You're also, going to provide a signal that says whether or not you're ready for more input, just like in lab 1, and you will pay attention to whether the downstream hardware is also ready for more input or not. So you've got a little bit of control logic to make sure you properly handshake. The filter coefficients are basically constants that we give you so they won't change during operation. So you've got a filter you can apply over the whole image. So that's another input, but you don't have to worry about it as much. You just have to pay attention to what is in the filter. But it's not going to stream in, it's not going to change as the image goes through. So anyway, you don't have to understand every detail of this because there is an assignment coming out, but if you have any questions, just put your hand up and let me know. Okay, so in lab one, some of you might have used IP cores, but probably most of you didn't. So I'll just point you at something additionally, something useful to know. So you could code everything in basic Verilog or system Verilog. That relies on Quartus inferring what structure it maps to. And that works well for like gates, multiplexers, registers, basic RAMs, right? So if you've got a RAM that's just a single port, right? You can do a read or a write, that's gonna work pretty well. Basic multipliers, all that stuff Quartus will just figure out quite reliably from HDL that you wrote. But if you start getting into more complicated hard block features, like you want to use more advanced features of the DSP blocks can do, for example, not just multiply, but also accumulate. They also have some dedicated interconnect to other DSP blocks. Generally, Quartus is not going to figure out how to use those from your HDL. Like it's a pretty specific pattern. You also may often find it easier to get things like FIFOs by just asking for them, right? You could make a FIFO by properly building a RAM and the read and write pointers and so on, but it's usually easier just to say, give me a FIFO that is hopefully, well, is well verified, right? Everybody has bugs, but there's not that much chance of a bug in that IP, so you just ask for a FIFO. Okay, so some of the ones that you would probably find useful, and again, this isn't the handout, but there's a menu called Tools, IP Catalog, and that's where you can see the IP cores that Altera gives to you as part of Quartus. There are a lot of IP cores there. The ones that are interesting to you are under DSP. You'll see primitive DSP, and you'll see there's one for every kind of device that Altera makes. So there's one for ARIA 10. ARIA 10 can do floating point. We don't care about floating point for this assignment, right? We're doing integers or fixed point. So you can ask for this DSP block, and basically now it has checkboxes for everything, right? And now it goes, well, this is what the hardware can do. What would you like? And you can kind of control every little detail of what the hardware does. Other ones that are going to be useful is under basic functions on-chip memory. You can ask things that could be useful to you in this. You're trying to buffer up data. You can buffer it up using shift registers, but these images are somewhat large. So I showed you on the chalkboard a while ago that shift registers start becoming inefficient in power and in area if you start buffering up large amounts of data in them. So you could get what's called a two-port RAM. A two-port RAM means you can read from it and write to it at the same time. It has two control ports, like two address ports. We're going to study how FPGA block RAMs are built later in the course, but basically those are quite efficient in an FPGA. The fundamental RAMs that are built in an FPGA are almost always two-port, and they are in ARIA 10. So this is a very efficient block. And basically you could say, I want a two-port RAM so I can read and write to it, and Quartus will make it out of the on-chip resources efficiently. You can also ask for a FIFO, right? So you just ask for a FIFO, or you ask for this two-port RAM. If you ask for a FIFO, it's like a more limited form of RAM. You know, you can put things in it, you can take things out of it. It has a read pointer and a write pointer, so it knows where's the next thing you're going to put in, where's the next thing you should take out. And Quartus will actually use either RAM or shift registers depending on how the size of the FIFO you ask for, so it'll automatically decide what it thinks is more efficient. So you just ask for the same thing, it'll optimize it for you. You're not going to need all these things. You don't need any of them. You can write this whole assignment without using any IP cores, just by coding it all yourself. But generally, you can get some additional efficiency. Like if you start trying for a pretty efficient implementation, you usually hit a point where it's easier to grab an IP core than it is to go recode more of this by hand. Yeah.
I have two questions. The first is, does Quartus tell you what's the maximum frequency that each IP core can run at?
These ones, that's a good question. Generally, no, but they have a data sheet. So if you go look for the product data sheet for the specific chip you're on, it will have a table of what's the frequency of all the hard blocks, okay? And basically this, you're actually instantiating the DSP blocks, so you will be limited by the hard block frequency. It's not just one number. It varies some based on the mode of the block. If you just run it, Quartus will tell you if you're limited by that block. It's printed out in a sort of weird way. It says min pulse width. Okay, min pulse width actually is a block limit. Okay, so whenever it says so frequency is limited in FPGA by one of two things. It adds up all the interconnect and logic and block delays, and it tells you this is the length of your data path, and this is your slack. And if your slack is negative, you didn't meet timing. So that's the thing that usually limits you, right? It's like adding up all the little bits of delay between registers. But if you make a very fast design, the other thing that can limit you is how fast can certain blocks toggle. So there's a limit on how fast the global clock networks can toggle. There's a limit on the DSP blocks. There's a limit on the RAM blocks. For the DSP and RAM blocks, it's not one limit. It depends on how many registers inside them you turn on. So it depends on the modes. So Quartus will tell you if you hit a limit. And it prints it in a confusing way. It says min pulse width violation limits you to this frequency. Min pulse width means this block can't go faster than that, okay? Min pulse is saying if you give me a clock that its clock high or clock low is less than this, I won't be able to cycle. So it's not the world's most user-friendly message, but that's what it means. If you don't want to just try things and see what Quartus says, if you go to this data sheet, it has all the limits, right? So you go look for ARIA 10 timing data sheet, and it'll have for DSP block, for every mode in this speed grade, here's the limit. So you can see what they are in advance. Same thing for memory. For this assignment, if you like pipeline really heavily, you optimize really well, you'll usually wind up limited by the DSP block in the end, because I think its limit is somewhat lower than the RAM block. But if you get there, it's good, right? And we definitely don't expect you to pry the top off the chip and start soldering and trying to make the DSP block faster, okay? So, okay, so hopefully that gives you an idea where to start anyway. I don't expect you to, I know this is pretty fast, so don't worry about having to memorize all these menus. It's in the handout too. Yeah?
Also in the previous slide where you showed what inputs and outputs we generate, do we
Yeah.
get like an input that's like, this is the size of the current image, or like the dimensions of the image we're working on?
Yeah, you're told the dimensions of the image. So you can write a little bit of control logic that knows when do I hit like the end of a row and so on. Does that make sense? We give you a full test bench, so like your code will test itself. Like you'll run the code, you'll know whether you passed or not. Does that make sense? So there won't be any like surprises of we're running tests that you don't know about. You know all the tests. Okay? Yeah.
For the coefficient, like because it won't change, usually like all the coefficients are the same, or
No, these 9 coefficients can be different, and for different test cases, we could give them to you different ones. But we're basically not going to change it as your hardware's running. Does that make sense? Like this whole image is going to pass through in one of the tests that the test bench runs. The test bench there are a bunch of different test cases you can run through the test bench. So there are small ones that are only like 3 rows high. You'd actually start by debugging with those, right? You always start with like the smallest test, and like there's some really simple ones. Like there's only one non-white pixel, right? So your output should be kind of easy to tell what your output should be. So you start with those really simple ones. And then one of the later ones is like an image of Jeff Hinton, right? And you're sharpening it up or something. So that's like, that is one, the test bench will tell you if you did it correctly or not, but don't use that as your first test case. It's a full image, it's gonna take a lot longer to run, and probably, well, lots of you have seen Jeff Hinton on the news a lot, probably none of you know what he looks like after going through a 3x3 sharpening filter, right? So I don't think anybody's memorized it to that level. Yeah, so, okay, and why are we doing convolution? Well, I guess I told you, convolution is super important. 1D is super important for signal processing, 2D is super important for image processing. And in convolutional neural networks, so one of the main classes of neural networks, we use both two-dimensional and what they call 3D convolution, but really what they call 3D convolution is just a whole bunch of 2D convolutions added together. So the heart of convolutional neural networks are 2D convolution, right? And instead of computing, one output image, what happens in a convolutional neural network is we'd bring in, say, 3 different colors, so essentially 3 planes of image. We'd run it through a whole bunch of different filters. So we'd produce a whole bunch of, that's what this is representing, a whole bunch of output convolutions, each of them over the same image, or in this case 3 images, but with different filters. And then we repeat that. Right? So we take all these things, we call them activations, but they're effectively the same size as the image, and we run more filters on them to produce more output activations and so on. And at the very end, if you were doing object classification, you'd go into something called a multi-layer perceptron, which is basically not convolution anymore. basically can be phrased as matrix multiplication. And it eventually would produce a bunch of probabilities of this being various things, like a car, a cat, et cetera. So what you're optimizing, I didn't want to give you like a full CNN to optimize, because it seems like that would be an awful lot for an assignment. But what you're optimizing is kind of the key operation that actually would go into a CNN. It dominates the runtime. And this is just, I like this animation. Let's see if it runs. Yeah, so this basically just shows the convolution running. Say on my input image, I'm basically taking the filter, and it's just scanning across the image and producing a bunch of output activations or output pixels. So there's nothing more to learn here, except this is just a cool animation that shows how a CNN is just a whole bunch of convolutions. What people call in a CNN a 3D convolution, it's not really a 3D convolution. It really means two-dimensional convolution, exactly like you did, but you do it on a whole bunch of essentially images, right, or activation planes, and you add them all together. So that's not really a 3D convolution. It's actually a bunch of 2D convolutions added together. The other thing people will do is they'll actually do a bunch of 2D convolutions, one on each of these image planes, produce a bunch of outputs, so a bunch of output image planes. So that is truly a bunch of 2D convolutions. You're not even adding them together. And then they'll do a 1D, and they call that a depth-wise convolution. And then they'll do a 1D convolution after that. So that's essentially exactly what I showed you in a FIR filter. That takes these and weights them and adds them up, and that produces your one output, okay? That's a somewhat less computation. So some CNNs do that. Instead of adding all of this 3D convolutions together, or all these 2D convolutions together, they just do one convolution per image plane, and then do another convolution in one dimension across all the image planes. You don't have to know all of that. This is like a super fast intro to convolution, which convolutional neural networks, just to sort of motivate, this is an important building block that's used a lot, right? Any questions on any of that? Okay, yeah, Alex.
Are FPGAs known for being very good at CNNs, or is it usually dominated by GPUs, or is it normally dominated by GPUs?
I mean, FPGAs are very good at convolutions. They're used a lot for image processing. And they're used a lot for like convolutional neural networks. I mean, GPUs are also good at convolution and also good at CNNs, so both are used. In the latter part of this lecture, I'm going to talk about FPGAs for deep learning, and then I'll talk a bit about GPUs at the end too. So FPGAs are good at it, GPUs are good at it. I'd say what you should use depends on where your system's going, what your power budget is, what else you're talking to.
Gotcha.
Does that make sense?
Yep.
Okay, background reading for next week. So basically, it's two of the papers that we're going to talk about today. So I'm going to use these as examples of deep learning on FPGAs. You can find a huge number of papers on deep learning for FPGAs. So you can go off and find way more of these if they interest you. But these two are ones that kind of highlight two different design approaches. And we're going to talk about both of them today. So you're going to have a pretty good idea of what's in each of these papers anyway. Okay, for reading for this week, so start off with one that's basically about how to do benchmarking well when you're doing throughput computing. It's a few years old, but I still think it's a really good paper, so that's why I use this one. And then one on how Microsoft deployed FPGAs in their data centers, which they still do. So this is still the basic architecture of, they've updated the FPGAs and so on, but the basic architecture of how they do it is still what's described in this paper. Okay, so where do we stand? So last week we were talking about FPGAs compared to a bunch of other devices in terms of strengths and weaknesses. And today's we're talking about two important use cases that are kind of interesting. So how do we put them in data centers? And how do we use them for deep learning? And obviously we use FPGAs for all sorts of other stuff, right? So you can use them like for all the things we talked about before, like I/O interfacing and communications processing and so on. But these are two pretty interesting applications that have become more important in recent years. Okay, so how many people read this paper? Good, most of you read it, excellent. Okay, let's see. Any overall thoughts? Anybody like it? Anybody really dislike it? What do you think?
I really like the fact that they tried to optimize both implementations. I think that's one of the things that, at least I was doing
took a grad course with Professor Jeffrey, and he wanted to do something, and that's one of the things that was communicated. And so seeing it actually applied in practice, that you're comparing again two optimized implementations against each other, rather than one unoptimized implementation, one very optimized implementation. And it's like comparing an apple and a banana. Here you're actually comparing two very optimized implementations. It feels more systematic.
I totally agree. It's a great answer, right? I hope you got that on tape. But yeah, I totally agree. And it sounds obvious, right? But the thing is, people often don't do it, right? They want to basically work on, I don't know, making an accelerated version of the following. So I spend 2 years working on that, and then I know I need a baseline. So I basically go out and grab some code and compile it the last day. And I don't know where I got this code from. Like I found it somewhere. I was on the bus, and this is my comparison, right? So.
Like it's a good baseline is important rather than just like the idea of like having a good baseline in the first place is pretty important.
Yeah, it's totally true. Okay, this is a digression, but I can't help it. Did anybody read? Okay, so I don't know. How many of you are in Jason Anderson's course? Okay, so quite a few of you. So you're interested in CAD. Igor Markov's a very well-known CAD researcher. He's at Synopsys now. He's at University of Michigan for many years. And Jeff Dean's a very well-known machine learning researcher and Google engineer. And they've had an extremely public fight, actually. It's unusual, not physical. I don't think they've actually tried to beat each other up. But it's like, and what they've had it over is there's a paper called Alpha Chip that was applying reinforcement learning to the placement of large blocks in ASICs, which is a difficult computational problem, and CAD tools often don't do that well at it. So engineers have had to do a bunch of that by hand. So Google published a paper saying they were using reinforcement learning and they were getting like superhuman results, better than humans could get. And then that paper became controversial, even within Google. So a person within Google complained, another researcher in Google complained that the team that did that work, which included Jeff Dean, had not done strong enough baselines. Like effectively, they hadn't actually fully optimized the traditional CAD flows. And this got incredible. Okay, so within Google, it kind of went bizarre, frankly, because he basically, I guess, made a bunch of noise about it wasn't a strong enough baseline, and therefore this paper, really, its conclusions were overly strong. So, okay, so if you're Google, how would you respond? They fired him. I'm not kidding. So, I mean, I don't know all the details, and I guess this is being recorded, but I guess I'm not going to Google. Yeah, so he fired them. They fired him. He sued Google. So this became very high profile. He sued for wrongful dismissal. Various people looked at the paper in detail. Igor Markov basically has a great article in the Communications of the ACM that talks about the paper and basically concludes that they didn't make it up, but it is probably overblown, right? They didn't have a strong enough baseline. So where they're claiming improvements, it's not clear there really are improvements versus the actual state of the art. Anyway, it makes for a very interesting read. So if you just go read about it, it's maybe a morality tale of this is maybe where things go really badly if you don't have a strong enough baseline. And so it's not just about even performance comparisons. That's actually trying to compare two algorithms and making sure that you compare to best in class and you're kind of careful with your conclusions. Okay, so the key thing that this paper showed is that they went through a bunch of papers, I think about 14 published papers, that had taken algorithms with a lot of parallelism and had put them on GPUs, compared them to CPU implementations, and they claimed about 100x would be a typical number from one of these papers. And the authors of this paper carefully went through all of these works and basically re-implemented them if necessary, got the original code if they could, and optimized them both for the CPU and the GPU. The GPU usually was already pretty well optimized because that's what the people have been publishing, but essentially they found the CPU code was often not well optimized. And then they recomputed the speedups, and they still found the GPU was better, right? So it had a performance advantage, but it averaged about 2.5x, and it varied quite a bit. Okay, so one of them had a still quite large advantage of 14.9, and 2.5x is not bad, but it's a lot less than 100x. And I guess we've already heard the key reason why. The key reason why is that a lot of the baselines just weren't that well optimized for the CPU. They just took a very simple approach for the CPU, And for the GPU, you actually couldn't do such a simple approach. Like I mean, they were well optimized. If you just kind of made a one-thread version of the computation for the GPU, its performance would be terrible, so nobody does that, right? They always put some more effort into optimizing it. So what were the key reasons? The first thing is they found that the lack of using SIMD was like a key problem with the CPU, right? So the CPU can do scalar computation without you really putting much effort. Well, you're putting some effort into your code, but you're writing sort of normal C or C++. You're not really thinking too much about the execution engines. So that's what a lot or all of these programs did. But there's a lot of parallelism in them that the GPU could exploit. Usually if the GPU can exploit it with a single instruction multiple thread, then a CPU can exploit it with SIMD because they're so close in programming model. So what they found is that the peak performance, this might be a bit small, but basically they're comparing a processor and a GPU that are about the same vintage, right? So everything moves in time. The key thing I think is to always just take something that comes from about the same point in time. The processor had 4 cores. The GPU had 30 streaming multiprocessors, essentially their core. The processor ran at about 3x the clock frequency. The GPU actually had more transistors. The GPU had more memory bandwidth, about 4 times the memory bandwidth. This CPU had a SIMD width of 4. The GPU had a SIMD width of 8. So both those nowadays would be wider, but the trend is probably still pretty similar. GPUs have somewhat higher SIMD width. And that's single precision. In double precision, it actually flips. GPUs are not very good at double precision. They just don't devote it. It's too costly. Double precision floating point units are really big. GPU just can't get that much gain, right? Like all of their tricks with SIMD and so on to amortize instruction overhead and be clever with the control logic gets somewhat washed out if your execution units are really huge. So GPUs don't emphasize double precision performance. So in this case, the CPU actually could do 2-way SIMD for double precision, and the GPU could do 1-way. And this is getting, I mean, I told you I'd talk about Blackwell today, and I will talk about it, but I didn't make as many slides as I thought I would. Blackwell's de-emphasized double precision floating point even more, okay? So they've just decided it's not where the bulk of the GPU market is, so they'll have a few units for correctness, but that's not where they're going for performance. So what that means is probably for this generation, comparing it single precision makes the most sense, and these algorithms could use single precision. So what most people were getting is they were getting the scalar floating point operations of the GPU, which was about 25 gigaflops, and they were getting the SIMD, or single instruction multiple thread, flops of the GPU, which is about 311. But if they put effort into using the SIMD of the CPU, it goes up to 102. Okay, so the difference in peak performance goes from over 10x to more like 3x, which is still significant. So anyway, they found that was they got a lot closer to, once they optimized, if they took the peaks of memory bandwidth and floating point operations, it gave them a reasonable guide of where could they wind up. Okay, so that kind of links into that paper that we studied last week on getting the peak performance of various devices. It is helpful in many cases to know what the peak is. They found it was predictive. But the GPU still has, I have 6x here, but when I do the calculation, I guess I get 3x, but 3x to 6x more floating point ops. It also has more memory bandwidth. So GPUs, there's no particular reason why a GPU has more memory bandwidth, except GPUs will spend more effort on it, right? They're using the same memory technologies that everybody else has access to, but GPUs are optimized for, they will spend a lot of money to get more memory bandwidth, and they also don't worry as much about getting as much memory capacity. So there's 2 things that limit your off-chip memory bandwidth. One is how much money are you willing to pay, right? If you buy more expensive memory chips, you devote more pins on your chip to it, so you make wider buses, you'll get more memory bandwidth. The other thing that limits you is if you need a lot of DDR, okay, like really high capacity, that generally means you need more DDR chips hanging off the bus, and they have to be further away. That makes it harder to clock them quickly, okay? So there's some trade-off between what is your capacity and how fast can you clock it. So GPUs go for, we will spend a bunch of money on memory bandwidth, and we will compromise on, we don't need to have like the huge memory capacity that maybe like an Intel or AMD server needs. The GPU has essentially smaller caches, right? Now they tend to be explicitly managed, but their on-chip memory tends to be less than what you actually have in a CPU. So sometimes that hurts them. To get performance out of the CPU, the first thing is, maybe I should have put this first, but SIMD instructions is kind of maybe the first thing that people are missing. You got to parallelize across cores. So clearly, if you're running a parallel GPU program, you shouldn't take just a serial CPU program, but sometimes people do that, right? They don't even bother to like multi-thread it. And if it's a very parallel program, that's not a very fair comparison. A little more complicated is a CPU doesn't have as much memory bandwidth, so it benefits a lot from blocking. Do people know what blocking means? Okay, who doesn't know what blocking means? So, okay, good. So anybody want to describe what blocking is? Go ahead.
I guess you want to organize your tiles or your data such that you can fit as much data in the cache as possible up front, so that when you go over data, you spend as much time going over what's in the cache rather than transferring it off and on chip.
Yeah. So you basically restructure the computation to make maximum use of your cache. Maybe the best example of this, or an example that I can think of easily, is let's take matrix multiplication, which we're going to talk about more later today. So if I have two really big matrices and I want to multiply them, it's basically take this row times this column, and that produces one entry in my output. Okay? So that is an order n calculation. I need to do that for this row times every column. Okay, so that makes it order n squared to get a row. And then I got to do that for every single row in this input matrix. So that makes it n cubed. Okay, so that's lots of computation. And if you look at the total amount of data, if this is n and this is n, I have two matrices. My input data is of order n squared. But my compute is of order n cubed. Okay, so that means matrix multiplication, I should be able to make it compute bound. There's way more compute than there is memory access, because I only need n squared memory and I need n cubed compute. But if you write this in the naive way, which is you write just 3 loops, okay? You're going to walk through this whole row, this whole column. Then you'll walk through this whole row, this whole column, and so on. So that means you're going to walk through this whole matrix for every time you compute one row, okay? Then you're going to go on to the next row of this, and you can do the same thing again. So you'll actually read this whole matrix n times. If this matrix is big, it's too big for your cache, so it means it's just going to stream right through your cache, right? You're not going to get any reuse, and you're actually going to read n cubed memory because you wound up reading this matrix n cubed times. So what blocking does is it says don't do it in this simple way. What you're going to do is you're going to say, well, to do a big matrix multiplication, I could basically compute some partial results here, like in this part of my matrix, that are just taking this piece of this matrix and this piece of this matrix. Okay, so they're not complete results. I'm going to have to add more data. I'm going to have to keep adding things, right? Because I've only added up this piece times this piece to produce a part of that. Okay? But what I can do now is I make it so that these fit in the cache. I can basically do this whole subcomputation, which has order, if this is like an m by m, I make it so that that'll fit in my cache. And I can actually do order m cubed computation to get all of the partial results that I need for this part of the matrix multiply. Okay? So what that can do is I'll still have to reload this a few times. Okay, I'll have to reload this. It turns out n divided by m times. So I'll have to reload it some, but a lot less. Okay, and that's what blocking does. You reorder. So your code looks more messy. Instead of having 3 loops, you wind up with 6 loops. Okay, a loop that basically computes a tile, 3 loops to complete a tile, and then 3 loops to go over all the tiles. So it's more messy, but it uses your cache a lot better. So this is an example for matrix multiplication, but you can do this blocking technique for a lot of computations. But you have to actually go and restructure your code. It is some work. Yeah?
So because CPUs have different levels of caches, so I guess you would do the same thing for each level? Or?
Yeah, that's a good question. So you could. You usually, if let's say your first level cache is reasonably big, Okay, so if your first level cache is big enough that you can make this this tile size, reasonably large. So now you can kind of use all your compute units. You're not limited by the speed of you're not limited by memory. And you can load the first level cache fast enough that, for example, the next tile is coming in, you're prefetching it while you're using this, then you might just tile for the first level cache because you go, the rest of it's okay, right? Like that was enough. I reduced my memory bandwidth to the point where it works. If you found, no, you don't have enough time to even like prefetch the next tile while you're still computing the previous one, there's not enough memory bandwidth, then you're right. Then you'd actually, you would still get further benefit if you did sort of a two-level blocking strategy, one that fit in the first level cache and one that fit in the second level cache. Which will make your code more messy still. So, yeah.
Since the cache is transparent to software, we're just kind of guessing that, oh, if I do this, this is what the cache will be doing based on the known size of the cache, right?
Yeah.
You can't actually order the cache to something.
If you look at CPUs some CPUs actually have, okay, so let's take a DSP processor. There you could tell the cache exactly what you want to do, but you're right, in CPUs it's normally transparent. Some CPUs do have like sort of low-level instructions to lock stuff in cache, so you actually don't usually do this, but if you're a real hardcore programmer or an operating system developer, you can. Most people wouldn't do that though. So you're right, you raise a good point of like CPU, so you go, well, I wrote the CPU code and it runs on a bunch of different CPUs. How do I know what blocking factor to use? So you might use one that you think is kind of safe, that you're pretty sure will fit in all the recent, say, L1 caches. That's one approach. Another approach that actually Intel uses in its math kernel library. So they have a program called math kernel library. It's a set of linear algebra routines that are highly optimized. And the first thing it does for a large linear algebra operation like a matrix multiply, it doesn't actually do the matrix multiply, it actually profiles the cache. So it does a bunch of instructions to figure out how big are your caches. And based on how big your caches are, it then chooses blocking factors and runs with those blocking factors. That is a very highly optimized library they spent a lot of money on. So you could do this in your own code, but it's going to take you a long time. So that's where you just go get math kernel library and use it. And it also is underneath some other libraries. Like Intel wrote this as like a baseline library, and then some other people build libraries on top of it. So even if you aren't explicitly using it, but you might be using it without realizing it. Like if you're using a machine learning library on a CPU, there's a pretty good chance that somewhere underneath it is actually calling into that. Yeah.
There's also some compilers that can actually detect the cache size and actually do this as well. And also, I think there's also a scheduler stuff that can also do it automatically. Keep the code looking clean.
Okay, that's interesting.
Yeah, just another way of doing it, but it's all the same thing, tiling, blocking.
I mean, the challenge of doing it in the compiler is you don't know what computer you're running on. So the reason that Intel Math Kernel Library does it at runtime is that they're compiling it once and running it everywhere. So, okay, so so blocking is another really big optimization. And then the last one, which is kind of application specific, and they only did it on a minority of the applications. Sometimes there's two ways to solve a problem. There's like the brute force way that's kind of easier to code, has regular data access, et cetera. And then there's a complicated way that's less regular, but is less compute. On a GPU, you usually will try to use, because it has a lot of parallelism, and the parallelism is both many threads and something very close to SIMD, you want pretty simple code, right? Like it doesn't really like complicated data structures and lots of if statements and so on. A CPU is better at that because of all that out-of-order hardware and all the prefetching hardware it has. So basically for some of these algorithms, they flipped to a more complicated implementation that essentially is a different algorithm, but gets the same answer. And sometimes that's better. That's kind of the hardest one, like making sure you're comparing against the best solution for that platform. And I guess that's what I'm saying here, in the same way. Like, so a GPU has higher parallelism, but some has a bit more difficulty with branching. It can lose performance faster with branching than a CPU can. So people try to minimize that, and that often pushes it away from the more clever code solutions. Okay, so what's the relevance to FPGA comparisons? So you already summarized it super well, right? You can't compare a hand-tuned FPGA implementation to the first cut serial algorithm on a CPU, but I see that people do that all the time in papers. Like not every paper, but just it's very common. Or they don't even say where they got the CPU code from. They just say I ran on the CPU. It must drive CPU architects insane. So don't do that. You'll drive them mad. Yeah, Raphael, did you have a question?
I noticed, because last week we had talked, or maybe 2 weeks ago, I don't know, like, about the, process being important.
Yeah.
And what I noticed that the CPU process, like the CPU they used in the paper was like 45 nanometer versus the GPU being 65 nanometer.
Yeah, so that does give them advantage, yeah. So that, I can't remember, did they try to normalize for that or not?
I don't remember.
So what they do have here is the number of transistors. So process technology is an important thing, but obviously you can also build bigger or smaller dice. So transistor count's another way that you could try to normalize, and the GPU has more transistors. So yeah, possibly they have an advantage because they're in 45. On the other hand, GPUs often have pretty big dice, so that might give them a counteracting advantage. Yeah.
Yeah, it's kind of also looking like at the top, it says it's from Intel, this paper, and they're comparing with one of their own processors. I wonder if there was a level of bias there. I'm trying to
Yeah, it's a fair comment. I think I thought the paper was fairly even-handed. They're pretty careful, but you're right. I mean, I'm pretty sure that like they probably didn't go in going, I don't care what the answer is, right? Like this just seems like an interesting side project. They were probably driven a bit, they were probably really bugged by these papers saying 100x, and they set out to show, we want to, they probably didn't want to go in and say, we optimized the GPU code and we got 1000x, right? So they probably were motivated to try to bring it down. But I thought they explained what they did, and it seemed pretty careful. It's a while since I read the paper, but I believe in a couple of cases they actually sped up the GPU code, because they also looked at the GPU code to make sure that it was well optimized. So that seemed pretty even-handed to me. So, yeah.
I just found it funny that if you look at the transistor count, like the average ended up being pretty close to the 2x in terms of the transistor count. Yeah. And another thing is like the power efficiency part.
Yeah.
Because I think the 960 they used, 960 they used was like 130 watts in terms of PDP.
Mm-hmm.
And if you do the math, it's actually less efficient than using the GPU.
Yeah, GPUs are not, I mean, they have a reputation for being high power, and they are, but it's partly because they'll push their power budget high, because they're trying to get high throughput. Their execution model, it's not a low power execution model, because they do tend to move a lot of stuff to main memory, but they can be more power efficient than the CPU too, like at the same throughput, because their execution units tend to be, like they're wasting less energy on control logic basically. So if there's lots of parallelism and everybody like kind of uses their hardware to the max, that favors a GPU. Something that doesn't favor them is they do tend to go to main memory more. So it's kind of a bit hard to predict. And yeah, and then on top of that, the way the world has evolved, and I'll show you this with Blackwell, is that people will pay for more throughput even if it takes more power. So yeah, there are some chips out there that are just massive, that consume enormous amounts of power. But the best thing to do is like kind of power, like operations per joule, right? Like what's the power efficiency? So, okay, so they did 14 benchmarks. And I guess I found it interesting too, they don't always get the same answer. So 3 of the benchmarks were memory bandwidth bound, and 2 of them, essentially they were predictable. They found that the performance ratio was close to the CPU to GPU memory bandwidth. One of them could use the CPU's cache efficiently. I can't remember exactly why, whether it was a blocking technique or what, but basically that means the CPU does better than just a straight comparison of memory bandwidth would indicate. 5 of the benchmarks were compute bound. So, meaning you can clearly see memory is not going to be as big an issue, it's just getting the computation done. And for those when performance was predictable by looking at like what is the data type and what's the peak performance of the CPU versus the GPU. And that there were 7 of the 14 benchmarks that were harder to predict. So I guess, yeah, why I found this interesting is last week we talked about that peak performance paper and what are the strengths and limitations of that approach. So in this case, they could have gotten about half. About half of the benchmarks they could predict from the appropriate peak ratio, and the other half they can't. So that's not bad, given that peak performance is not that hard to compute. If it gives you good guidance half the time, it's not a bad thing to do. But you obviously don't want to use it as the sole thing you compare, since it only got about half of them right. And let's see. Any other thoughts on this paper? Yeah.
So a lot of the hardware suggestions they had, like how to improve CPUs and how to improve GPUs, have actually like also have wider SIMD. GPUs can do better synchronization nowadays. So a lot of things architecture-wise have changed, which kind of make makes their analysis of why CPU and GPU performance differ for like this specific benchmark kind of invalid at this point. Like obsolete, right? So like for one, they say like, oh, the CPU doesn't support scatter gather instructions, but they do now. And for another one, they say, oh, GPU can't do synchronization that well. That's why it's slow. We need to launch multiple kernels. Nowadays, you don't need to do that anymore. So I wonder, like, how the results compare like now.
It's a good question. It would be a lot of work, but you could update it, right? It might be a great paper.
Luckily, you're his student.
I think, I mean, that's true. I think, though, that was some of the, I think the basic conclusion will still hold. Make sure you optimize for both. Make sure, like, if you don't do SIMD and multi-threading and blocking, you're kind of not doing a fair comparison. GPUs are trying to address, some of their weaknesses on synchronization. I don't actually know. I mean, CPUs are pretty good at synchronization, so I don't know if they've caught up or just kind of gotten closer.
It's not as good, but for example, something they said is I can't synchronize between like a different SM and I need to like launch another kernel to do that synchronization. NVIDIA did add support for that like 5-something years ago.
Yeah. So some of that. So it makes sense. But I think their number, I guess the big picture they got was don't neglect SIMD, don't neglect blocking, don't neglect multi-threading. CPUs have increased their SIMD count, so has GPUs. Where would that wind up now? I'm not sure. Do you know what I mean? They've both increased their SIMD significantly. The ratio is still that GPUs have more SIMD. They go typically now 128, and CPUs are maybe 16. Okay, if you take like a high-end CPU and a high-end GPU, that's a difference of a factor of 8. That may be a wider difference they had here. Because here on single precision floating point, they had a difference of a factor of, I think, let's see, what did they have actually in the end?
4 versus 8.
Yeah, I guess the fact that they had, but I guess the other thing is the cores on this GPU haven't gone up as fast. So I guess that makes it a bit complicated. CPU cores they haven't gone as aggressive on widening SIMD. They've widened it by a factor of 4, but their core counts have gone up by quite a lot. The latest in GPUs, their core count, their SM count is maybe 120. So it's kind of, I guess, difficult. I don't think the peak performances have diverged enormously. They have diverged some. I think the GPUs are pushing the peak performance a little more aggressively. There's another thing that's happened, which I'll talk a little bit about with Blackwell. But basically, GPUs have been more aggressive at going to lower precision data types. Where they can get very high degrees of SIMD is if you push the precision down. So at this point in time, most compute was done in single precision floating point, both for the GPU and the CPU. And now for machine learning, probably the most important workload for both of them, well, certainly for the GPU, the workloads they're pushing the precision down, right? So you're going to basically be doing training 16-bit floating point and maybe 8, but 8 is a bit harder, 16 safe. And you're going to do inference in 8-bit floating point. 16 is easy, 8-bit's pretty safe. And they're even trying to push below that. So GPUs have been more aggressive about pushing to lower precision data types, and that's where they're getting some extra SIMD gains. Yeah.
I wish the paper kind of like discussed the value proposition of doing the actual optimization from the programmer standpoint, because I know like you can do like blocking and multi-threading and SIMD utilization, but I don't know. At the same time, as a programmer, I can also say, okay, I can also just use a GPU and do like numpy.multiply matrix, just.
Yeah. So I think that's a really good point too. So something they don't talk about is the difficulty for the programmer. And this is where we talked a bit about this last week, that SMIT mixed with NVIDIA's built a very nice software stack on top of it, seems to be easier to program than SIMD, right? The CPU vendors don't seem to have done as good a job. The compilers can use it some automatically, but to get the most out of it, you usually have to put these compiler intrinsics in your code. It's a pain, it's low level, and then the binary actually won't take advantage of wider SIMD without recompilation. except in RISC-V. RISC-V is doing it differently, where they actually encode the vector width, like the vector linked in the instructions. So they're trying to avoid that. So I agree with you. It's hard to say. It would be an entire other paper, but it's like, how hard was it to get this performance? And I think they went from, before they did this, the CPU implementations were clearly easier, right? People just kind of, they grabbed some code that was like serial C and they ran it, right? Or maybe they did a bit more. After all their optimization, my guess is the CPU code was actually harder to optimize, given the programming model available. So that's a good point too. Some of if you use NumPy though on a CPU, it will be optimized. It won't get as much as the GPU because the GPU is higher throughput, but NumPy on a CPU is going to be using things like under the hood that are highly optimized as well. There's another thing that happens, which is now a business reality. If you become dominant, okay, so for a long time, Intel and AMD were dominant in the compute space. So fighting against them, you were always fighting against the software compatibility with x86. In recent years, for at least ML, that's flipped, where NVIDIA is dominant, and that means people optimize for NVIDIA first, okay? So you will get optimized libraries for a CPU under NumPy, but they're probably not as optimized because the first thing NumPy is going to try to optimize is the GPU code. And NVIDIA appears to now have all the money in the world, so they also have all of their internal developers. So, you do get some positive momentum, where it's not just about, is it technically easier or not? It's like, how much money can you spend? And how much payback will you get? So, and that affects everything. Even you think of what machine learning models become dominant, machine learning researchers are running them generally on NVIDIA GPUs. So whatever models run well on NVIDIA GPUs also become the models that people tune on the most, which gives an additional boost. So there is a lot of incumbency advantage too. Yeah, any other questions or comments on that? Yeah.
Plus, NVIDIA can just take the most recent models published, which they already run on NVIDIA, and test their new chips to see if it's even better.
Yeah, that's totally true. Who was telling me about that actually? I think it was Andrew Putnam from Microsoft. So actually, you're going to see some slides from him. So Andrew Putnam is a senior person at Microsoft, and I was asking him about. So Microsoft, you can see what they put FPGAs in their data centers. They use those for a lot of their infrastructure. They also now have a lot of GPUs. And I was asking him, you're spending so much money on GPUs, why not buy more AMD GPUs? Couldn't you get a better deal? And he said, yeah, they could. But NVIDIA has this big advantage over AMD right now, even though AMD from a high level is kind of, they also make GPUs. So kind of the closest thing in programming model, which is that all these machine learning researchers, when they publish a paper that has a new model, it comes with code, and that code runs on an NVIDIA GPU. NVIDIA can download them. They can test which one of these models seem to work best. They go, that one, I love it. Let's tune for that. And AMD or anybody else has to find, there are 100 papers published that say they're all the best. And instead of just running it, they have to go try to validate that, then try to rewrite the model for their hardware, then see how would we tune this. That's just a fundamentally much slower thing. So yeah, there's a lot of things that are nice to have at NVIDIA now. Yeah.
So I'm curious how NVIDIA got this dominant position versus AMD, formerly ATI. Why did they get that early lead versus AMD?
Because CUDA, they've executed well on the hardware, but CUDA is probably the really big differentiator. You'll see in the FPGA industry as well. People have to make good hardware, but they usually underestimate the importance of software. Jensen Huang is, I'm going to go work at NVIDIA. Jensen Huang is a very smart person, right? So I've eliminated Google, but I've totally put my resume in for, I'm not really. So actually I'm working at Cerebras, I shouldn't say that. But NVIDIA is a worthy competitor. And Jensen Huang is a very smart person. So I went to a great seminar here when I was still at Altera, but I came to this seminar at U of T where it was a prof from the University of Illinois who had made the first programming course using CUDA. Okay, so NVIDIA made CUDA as an internal tool initially to make their device drivers. And NVIDIA had very good device drivers. It was a competitive strength in the graphics market that their device drivers tended to be highly performant and stable. And apparently, it was because internally, part of it was internally they were using CUDA. They had this nice technology of how to write device drivers. And then, I don't know who in NVIDIA did this, but Jensen Huang certainly jumped on it, or maybe it was his idea. People started writing OpenGL code to do computations on GPU, which was painful. You had to actually pretend you were doing graphics, and you wrote graphics code, but it was really like a field solver, right? And you can imagine that it's kind of a nasty problem. So Jensen Huang partnered with his prof at the University of Illinois to create a course to teach people how to program in CUDA. So he opened up CUDA. First, it revealed its existence. You could program in it. And he flew in his private plane every week to Urbana-Champaign, which is where I did my master's degree. So I was like, oh, this is kind of cool. I wasn't there, but I still thought it was cool. And he co-gave the lectures, right, with this professor. And then this professor came to talk about that experience here at U of T, like after the course had happened. So that was really visionary, opening up something which apparently was controversial within NVIDIA, because it's like you're opening up some of our secret sauce. This will teach competitors like AMD how to write device drivers the way we do. But by opening it up, they basically became the incumbent in this emerging market for computation on GPUs, which at that point was not a major market at all. And he created a course with an academic to show people how to do it. It wasn't enough just to open up the source. They actually made training materials. And like your CEO is flying in to co-lecture a course at a major research university. So it's actually kind of pretty amazing, right? I can't imagine too many CEOs doing this. And so that's, people started using CUDA, and then machine learning took off. So now you have all the ingredients in place, and then NVIDIA's executed extremely well since then, right? Like they haven't paused. They've done a great job extending their software and their hardware as well. But I think that's the key thing that people are struggling to overcome, like particularly AMD, because from 1,000 feet you would go, it's a GPU, it's another GPU, the programming models are going to be very similar, but they don't have CUDA. Yeah?
Just like on the same topic of software, like from a business standpoint, both NVIDIA and the CPU vendors, they sell like the average application, right? And the average CPU application and the averagely written GPU application, the difference between them is somewhere between 100x and 2.5x, right?
Yeah.
It's not that extreme, but it's not the other extreme as well. So I think that's why this paper didn't tank NVIDIA's stock, because they're not selling to the hyper optimizers. They're selling to most of what they're selling is like in between.
And I mean, 2.5x is not a bad result. To be honest with you, 2.5x.
Like Bernstein pointed out, like for the power that like extra power consumed, maybe 2.5x would not encourage you to buy a GPU. But
Yeah. Yeah.
The 2.5x number also includes some benchmarks where like the CPU is better, but like most customers have a like use case in mind where they like every computer needs a CPU, but not every computer needs an accelerator like a GPU or FPGA. And like you would only buy an accelerator if you have a use case where you would see like a worthwhile acceleration from the like accelerator, right? So like the 2.5x number, I don't think would guide people to say, I probably shouldn't buy a GPU
Yeah.
because it's only 2.5x better. They would look at their application and see, oh, it's actually 10x better for my specific application, and therefore I should get a GPU.
Yeah, that makes perfect sense. Okay, let's move on to the next paper I had. Well, it's actually two of them. I'm going to cover both these. This one you were supposed to read, this one you could read if you wanted. They're the kind of the evolution of this system at Microsoft. So these are, I think, two really interesting papers. How many people read at least one of these papers? Did you like it or not like it? Okay, maybe that's too vague. How many people liked it? How many people did not like it? Well, there's a couple of people didn't like it. Okay, why did you not like it? Sorry to pick on you, but that's an interesting answer.
I think because I didn't read the first one, reading the second one felt like I was missing some episodes of the season. So it wasn't very fun.
Yeah, no, that's actually a good point. That's kind of why I struggle with this. Like, this is what they do now, but this gave more of the backstory. So it's kind of like if you kind of stuck these two papers together now, you'd probably wind up with an even better paper. Here's the things we're thinking of, and here's what worked out well. So that's a good point. So, okay, so so Microsoft started a project quite a few years ago now to see could they use FPGA acceleration. And the lead use case they wanted to work on was Bing search engine optimization. So Bing is Microsoft's competitor to Google. It probably might drive Microsoft nuts that I feel I have to explain that. It's pretty widely used, but not nearly as widely used as Google. Well, I think they still have like 10%. They have 10% of the search traffic anyway, which is still a lot. Okay, so it's a complicated algorithm. It's deployed across thousands. They wouldn't tell me how many thousands, but it's many thousands of servers. Okay, so what's interesting is the scale at which they do things. And what they want to do is they want to reduce the cost of the computers, the power consumption, and they don't want to increase search latency. So it's throughput computing in the sense that they have, millions of people doing searches, but with like a latency bound, because people just give up if it takes too long. And it's not just the average latency, they don't want the tail latency. They don't want to lose like 5% of their users every few hours because the latency for them was bad. They need a really scalable and reliable system. So what they call a data center class. So it's not okay for a data center to go down. So they have a reliability constraint that's much higher than most systems. And the reason they looked at FPGAs is because Moore's law is slowing down. For many years, it was hard to get accelerators into data centers because you just got the next CPU. And by the time you had the code running on the accelerator, it was already a generation or two behind, and the CPUs had caught up. So for a long time, it was hard to make progress against that. But as Moore's law has slowed down, kind of need to push harder to get gains, like recode things, try different things. So I stole some of these slides from Andrew. It's just interesting, what does a data center environment looks like? So it's massive scale, so hundreds of thousands of servers. So I think I told you guys like a few years ago, I asked how many servers, and it was clear that it was more than 1 million, even though they didn't want to tell me the number. But by answering yes, no questions, they told me the number. But it's growing fast. At that time, it was growing 30% per year. So I don't know how many millions it would be, but I assume it's in the millions. So it's huge. Power and space are scarce. They're mostly unmanned. So data centers apparently are so hot that you actually can't send people into them easily. So Andrew told me that when they send people in these data centers, at least in this time, their data centers, they have to send them in like firemen or firewomen equipment, right? Like heavy jackets and stuff to protect them against the heat, and they can only handle it for a while. Individual servers frequently fail, and they might be repaired, they might not be. They'll often just leave them, and when they basically decommission that part of the data center and upgrade it with new servers, they'll take them out. But they're not going in and fixing individual machines as a regular thing. And the overall availability goal is basically 100% minus epsilon. What do their servers look like? So they have a standard, the Microsoft Open Compute Server. Probably evolved some since these slides, but they're really trying to pack them in tight. So 1 unit high, so like that high, half unit wide, so like that wide. They have enough, and these servers have enough space and power for, at that generation at least, a half height, half width PCIe card. So they can squeeze in an FPGA without taking out one of the 2 CPUs, and they have lots of stuff running on these CPUs. They don't want to take out one of the 2 CPUs. They could not fit a GPU in, they could not power a GPU, okay? So the main thing they're optimizing for is performance per watt per dollar. So they care about energy efficiency. It's about 30% of their overall cost at that time was power. And they care about how much it costs to put it in. So they combine everything in that metric, and they say that's kind of their first order metric. So there's not going to be much maintenance, so they can't have things going down and people monkeying around with it. FPGAs, often people have like these little FPGAs on their desk, and they can actually program with a cable. They go, you can't do things like this, right? Like it all has to be over PCI Express. No person is going in. The machines last 3 years. They buy new ones every 6 months. Those are now state of the art. They get the high-end services like Bing. After about half of the way through their lifetime, they basically get moved over to less speed critical, less profitable, less mission critical services. So they get about 3 years of use out of them. I had lunch with them recently. He said because Moore's law is slowing down, they can actually sometimes squeeze this to stretch this to 4 years. But it's basically about the same. You're state of the art for 18 months or 2 years, and then you're okay for another 18 months or 2 years, and then you're just not worth the power after that. And they unplug you and replace you. And homogeneity is highly desirable. They can't 100% achieve this anymore. So Microsoft has lots of GPUs now. But they don't like things that are different. The reason they don't like things that are different because it's a reliability risk, right? You make something different and you have that thing could break and you need to fix that thing. You can't fail over to just one of your other million things that are exactly the same. It's also becomes something that your engineers have to understand, right? Like a homogeneous thing, you just say, I have 1 million of this, right? I don't have I have 100,000 of this and I have 50,000 of that and so on. Like it's much harder to keep that all running and program it. So they'd really like to be homogeneous. Okay, but the most homogeneous thing is just have infinite CPUs, but they found that was no longer efficient enough, okay? So they're having to back away from that, be perfectly homogeneous, but they're doing it kind of reluctantly. They'd rather not. Okay, so what they'd like in data center friendly FPGAs, they should fit into existing servers, low power, so all the power should be drawn from PCI Express. That's what they wanted. It means they're not going to buy the biggest FPGAs. They're going to buy kind of mid-size ones that are kind of more cost efficient, because you get into the biggest ones, then you pay a lot of money and their power consumption goes up. And they'd like to not be limited to like using one FPGA or something. Like they don't think at those scales. They think on huge scales. So the first generation of this project was called Catapult. They built this small FPGA. Let's see, where is it? It's a small FPGA card that they then insert in this server. This is the whole server. So it's got 2 big CPUs. It's got a bunch of hard disks. And it's got a relatively small FPGA card. They didn't have to take out any CPUs. They plug it into the PCIe slot. It took 25 watts, which they can power through PCIe. It doesn't need a separate power connection. It's easy to pull in and out. And what they do is they obviously are arranging these servers in racks. So a half rack, so halfway up the height, will fit 48 FPGAs. And in Catapult version 1, they arranged these in a 6x8 torus. So does everybody know what a torus means? Right? It's like a mesh, but with wraparound connections. So you talk to your nearest neighbor, but if you're on the edge, you talk all the way over to the other side. So 2D connectivity structure. And they used 20 gigabits per second serial links. They wanted low latency, so they used the serial transceivers of the FPGA, but they built their own lightweight protocol on top of that was more efficient than using existing protocols like Ethernet or even heavier weight stuff like TCP. Okay, they want basically people, they're taking mostly software developers and saying, some of you should start using hardware acceleration. That's already like kind of a bit uncomfortable. And they couldn't just take software and make hardware, but they have to now work with hardware developers. To make it easier to put in this application logic that's going to accelerate some part of a computation, they wanted to isolate it from all the I/O. So a bunch of an FPGA's value add is the I/O, but that's also where you get a lot of kind of tricky timing, right? We talked about talking to DDR. And you talk to an IP core, and you configure the IP core, and it'll eventually talk to DDR, but if you misconfigure something, it's not going to talk to DDR. And they don't want individual application developers worrying about that. So what they did is they designed something they called the shell. Okay, so the shell is basically all the I/O and all the management. So it had a couple of memory controllers to DDR. It had PCI Express. It had a DMA engine, so you could just say transfer this data at a higher level protocol that would do it. I told you it had these serial links to the other FPGAs in this torus, your nearest neighbors. So there's an inter-FPGA router that you talk to, and there are these serial interfaces that they've configured and developed, and some management interfaces for just resetting the device and so on. They basically designed this once, and it took actually a fair amount of logic. 23% of the logic at the time was a mid-sized FPGA, 500,000 logic elements. Inside tools like Quartus or Vivado, so they're using Quartus, you can basically create what you call design partitions. So design partitions means take this part of my design and do not optimize any logic out of it or move it out of that. So you're not allowed to make any. You have to treat this part of the design as being optimized by itself. I want you to place and route it in the following region, and then I want to lock it down. So you can lock down that design partition, meaning you stay exactly where you are. You use exactly the wires you're currently using. Everything else that I put in here has to just work around you. What that means is they basically closed timing. They not only designed the RTL and the IP cores, they basically compiled them till it met all of the timing constraints. They tested in system, and then they lock it down. So it did cost them, this logic, but now basically everything, all this tricky timing is handled, and their application developers don't have to worry about it. So they're the first team that I saw do this, and they defined this term shell that now you'll see widely used in the literature. People will talk about they have a shell, and Microsoft called it the role. The role is basically the application. So this separation became kind of common, of take the tricky timing parts and lock them down. Okay, so their application that they were really interested in was this Bing search. The algorithm, the core of the algorithm was too big to fit in one FPGA. So what they did is they basically made a pipeline that, like the whole thing is a big pipeline, but they split some of the coarse pipeline stages into different FPGAs. So CPU basically injects Bing requests, right? So search requests. And they never revealed all the details of exactly how Bing works. But basically, they have some features, some machine learning, some scoring, and that goes around in this pipeline. Now, they have this two-dimensional torus. They actually only needed 7 FPGAs to do one instance of this Bing accelerator. So they didn't use the whole torus. They used it as like a ring, right? So they used like one dimension of the torus. And they actually used 7 of the 8 FPGAs so that one of them was a spare. So if one of these FPGAs wasn't working, they could program it as a pass-through, and it would just pass its inputs to its outputs. And as long as it could do that, they could still use the ring, because they were only using 7 out of the 8 things. Let's see. And they have to have it detect. So everything's about reliability. So they have to actually detect if any FPGA is going crazy. And if it does, housekeeping software configures that one as a pass-through and moves all the other ones over. So they have kind of layers of redundancy. They also update how this search algorithm works all the time. So these free-form expressions, which are them extracting some features from your queries that will then go into some machine learning models. And again, they've never said exactly how this all works because they consider it pretty secret. They felt the most efficient way to do that would be to build specific hardware, like build hardware that did only those exact expressions, but it would take too long for at least their application developers. So they basically made a data path that was good at this, and they controlled it with a finite state machine. And the finite state machine, they didn't have to build by hand. They made a domain-specific language where you could describe what you wanted, and they could compile that and make a state machine for you. So these free-form expressions, they basically use the programming model of a custom data path controlled by an FSM. So FSM with data path, one of the design styles that we talked about in the programming model. And to make it easier, they made a domain-specific language that would automatically build the FSM for you. Okay, so what did they get? So they were really happy with the results. Okay, so they got a 95% improvement in throughput at the same latency. So they only care about getting answers as long as they meet their latency constraint. So they could get almost twice as much out of their servers. They made that better when they went on to Catapult v2, the next paper. So they actually now got to 125% throughput improvement. The software is actually the limit. They didn't move the whole algorithm to the FPGA, so the hardware more than kept up with the software. So it more than doubled the throughput by moving a lot of the stuff off the critical path. I know Andrew was interesting. He would talk about, he'd present this at conferences, and this I think is great work because of the complexity of like the system. But he'd say academics, I don't think he was including me, right? But, but they would review the papers that they were sending in, and they'd say, you only got 2x, right? Like I thought you'd at least get 100 or 1,000. And he goes, you don't understand, like in a production system, like Bing and Microsoft's data centers, that like people work for years to get like a 5% improvement. Like this stuff, if you're going to get 100x and so on, like this does not happen, right? So he goes, the management was incredibly excited about this. So you have these academics who were kind of going like, come back when you got at least 10x, right? so it was interesting though. It actually, yeah, I had similar experiences at Quartus. Like Quartus, we would micro tune and so on. And you get like it to be like 5% better frequency. And you go, this is an unbelievable release. And sometimes you're talking to an academic, they're like, couldn't you get like at least 50%? It's like 50%, right? I'll be CEO if I do that. So, okay, they did this with less than 10% power increase per server, which is why they're excited, right? So their power efficiency got way better. They couldn't do this by just buying more servers. So this was very successful because this prototype, and it's interesting, their prototype was, I forget it was 1,000, I forget how many machines it was. It was something like their prototype was, I believe, something like 2,000 servers. Okay, so the scale at which they do things is pretty interesting. Based on that prototype, Microsoft went, well, that sounds good, do it. So they basically said an FPGA in every single server, which they still do to this day. So this is, so they scaled it across the entire Bing part of the cloud, and then the next generation, they just did it across their entire cloud. Okay, so that was Catapult v1. And I guess it was deployed, as I said, across all of Bing, which is tens to hundreds of thousands of servers. But Catapult 2 was deployed across the whole Microsoft set of data centers, so into the millions now. So what they did in Catapult 2 is they decided basically they didn't like that Taurus switch. Okay, so they said it was like a maintenance problem. They've got this custom cabling nest that is like a failure point. And they've basically got a new thing to teach their developers. You have this Taurus that you can communicate with these 48 things more efficiently. That's hard to teach them. So what they did for Catapult 2 is the way their whole data center is made is you have all of the servers in one rack go to a top of rack switch. So they can talk to each other by going through like one Ethernet switch. If you need to go outside of your rack, you go to a level 1 switch. And that covers like some fraction of the data center. I don't know, say a row or a piece of a row. And if you need to go across the whole data center, you go to an L2 switch. Okay? And each of these adds latency and there's less bandwidth. What they wanted to do is basically make the data center look like you have a plane of compute, all these CPUs that can collaborate through these switches, and now also have all these FPGAs that can collaborate through these switches. That's like an easier abstraction for their developers. And it also enables more programming, more co-processing styles. So in Bing, what they did is the CPU was connected to everything else and brought in the requests, and then the FPGAs kind of worked on them and sent it back to the CPU. So it's like a CPU offload model. The CPU talks to the rest of the world. They still wanted to support that, but they also wanted to be able to support just the FPGAs collaborating amongst themselves without the CPU being involved. So the CPU could be doing something else, right, a different application, and the FPGAs could be doing their own thing. And you could have a different region of CPUs doing one thing, a different region of FPGAs doing something. And they have an interesting paper on this where they basically did data center scale machine learning, where they basically have huge numbers of FPGAs collaborate by each taking a piece of a machine learning model, and it's spread across, and they all collaborate over the network and act like one giant FPGA with less bandwidth between them. And the last thing they wanted to do, which turned out to be their most important use case, is bump in the wire. So bump in the wire means all the data coming in to the CPU actually goes through the FPGA. Okay, so the way they connected things in Catapult 2 is they kind of flipped things from the CPU connects to the network and sends data to the FPGA, to the FPGA connects to the network and sends data to the CPU. And what that allows them to do is what they call bump in the wire processing. So data can come in and they could decompress it before sending it to the CPU. Data could go out and they could compress it before going out to the rest of the network, which makes the whole network more efficient. Or it makes their solid state disks more efficient. They can encrypt things and decrypt things on the fly. So there's a lot of sort of streaming computations that happen where if they're in between the CPU and the network, they can just do those right on the fly. Okay, so they flipped how things are connected. This chart is comparing what they did in Catapult 1 versus Catapult 2. Okay, so this red line is, this is like how many FPGAs or hosts, like CPUs, I can reach. And what is my latency? So in microseconds. So this is what they got in Catapult v1. So they have this Taurus, and they could get to 10 different FPGAs in about 2.5 microseconds. And then they could get to about 48 in about 10 microseconds, because they have to go through more and more hops on the network link. If they use this new strategy in Catapult 2, they have to, for any FPGA in the same rack, they have to go through an L1 switch, and it's pretty fast. It's maybe only 3 microseconds. If they have to go to more than maybe 20 or so, then they have to go to an L1 switch, like the next level of switches, and that's slower, maybe 7.5 microseconds. And if they want to go to the whole data center, they have to go through one more switch, and that's slower still, maybe 17 microseconds. But what they found is the Taurus was only a little bit faster, basically for things very close. And then for things that were further, it was around a tie, and then it just couldn't get you there. Okay, so this is kind of more scalable. There's never a point where you can't talk to something. Now, at this point, Catapult v1 would just go to the CPU and ask it to go to the network. So it's not like you can't talk to the rest of it, but you have to sort of switch to a different mechanism of communication, so it's more complicated. So they liked the scalability of this, and they basically didn't lose much latency, even for things that are really close, because Ethernet switches are fast. And I guess I already mentioned this, right? So they get rid of all this torus wiring, which they found to be a pain. Data centers have wires everywhere, so they don't want it, they'd like to get rid of them. Latency wasn't much worse for things that are close by, and it's easier for the developers to understand. Because the developers already understood this, right? This is how the CPUs always communicated, so their parallel developers already had to understand this. It's not a new concept. So in Catapult 2, they still use this shell where they do all of the I/O and housekeeping and everything processing, but it actually got even bigger. It became like 44% of the FPGA because they put higher speed networking into it. So one of the things that Microsoft has been pushing for is basically take what's in their shell and put it in hard logic. So this has probably gone back down since then because they are, like when you're buying millions of pretty high-end FPGAs, you become a powerful customer. So when they ask for like, could you harden this for me, they've got a fair amount of sway. But it's interesting, the shell is kind of ripe for optimization in this system at least. So the FPGA is between the CPUs and the network, so it's a smart network interface. So you hear the term SmartNIC sometimes. And yeah, they can process data going to and from CPUs. So compression, decompression is a big one. Encryption, so there's a part, so Microsoft's cloud that they will rent to you. They have part of their cloud is just running their services, Office 365, all the OpenAI stuff, whatever. Another part they will rent to you if you're a big company as Azure. And a piece of that is called Secure Azure. And Secure Azure, everything's encrypted, right? So the data that goes between servers is encrypted. The data that goes to the solid state drives is encrypted because the companies, they don't ever want a data leak, right? They don't want Microsoft to see this data. They don't want anybody to leak it. So that's a lot of encryption and decryption as you're moving all the data around. So it's a good use case for these FPGAs. And I was talking to one of the engineers who worked in Secure Azure, and it was pretty interesting how secure it is. So they have 2 levels of keys, like kind of a master key, and then, I don't know, like another tier of keys. And you need both of them to work together. And sometimes a company has to go update its keys. And when they do that, they actually have to, they'll have to, like a couple of people with subkeys show up. They have to show up. The protocol is they show up in different vehicles. They go into a physically secure facility, like literally like armed security guards and like, bars. And then they go in and they stick their keys in, right? And they update something. So they don't have to do that very often. But I thought that was kind of interesting, right? It sounded very like Mission Impossible kind of. So, yeah, okay. And in this Catapult 2 system, the FPGAs can now communicate amongst themselves without getting the CPU involved. So they can also do kind of more scalable offload. They don't need, you can have different mixes of CPU and FPGA. One of the things they worried about is what if the FPGA goes down? So the FPGA goes down, you've now disconnected the CPU from the data center. If it's one CPU, it's not a big problem. If it's like all the CPUs, this is like probably a career decision for somebody, right? Like the CEO is going to notice that the data centers are all down and might ask, who took the data center down? So they're really worried about this. So what they did is in Flash on the board is they make a safe FPGA configuration. One that's been really validated, does really basic functionality. It just connects everything to the network so that they can always reboot off of that. And if things go wrong, it reboots off that and reconnects you to the network. So, yeah.
I was wondering, could they have added a direct connection between NIC and Core so they can bypass FPGA when it fails?
They could, I guess then it's like, what is that chip? So now you have that chip that could fail. Do you know what I mean? So if they add like a direct connection as well, that's another network interface card. So they could have a fail-safe like that, but they have to worry about what if the fail-safe breaks? Does it take the FPGA down? So anyway, yeah, this is rolled out to all the Microsoft data centers ever since then. Okay, so a few more thoughts on data center prospects for FPGAs. So there's a company called Netezza. What they did is they put FPGAs in the data path to a solid-state drive. So they did on-the-fly compression and decompression and management of basically all the sectors on a big flash drive. And they did the first level of basically database processing. Database processing tends to have all sorts of filters that get concatenated. So they basically did the first level of filtering right on the solid state disk drives without ever going back to the CPU. The FPGA would just do a very data parallel check of, is this data I might want? And they sped up database searches by 10x, and IBM bought them for that. Another use case has been these data processing units or infrastructure processing units. So that's kind of what Microsoft is doing internally. That's their key use case at this point for the FPGAs. So as I said, it's compress, encrypt, packet inspection is checking there's no nefarious traffic. It's also very data parallel. And there are external companies that do this too. So there's one called Mango Boost that a bunch of U of T people have gone to as well, where they make these data center processing units, not for their own data centers, but basically to go sell to Microsoft and other cloud providers. And they use FPGAs to do that. And it's led to so it's the main reason that, at least the stated main reason that Intel bought Altera. Now Intel has since partially IPO'd Altera, so it may mean that that stated plan didn't 100% work out the way they wanted. It also appears to have been a big factor in AMD Xilinx acquisition. So it's become a major market for FPGAs, but I actually haven't seen a breakdown of how big it is compared to the traditional communications market. It's clearly significant. I don't think it's actually taken over from the communications market as the biggest one. Okay, last thought on data centers. There's a few different ways you can connect a CPU and FPGA. So Catapult says connect the FPGA to the network, then connect the CPU to the FPGA. But how do I connect the CPU to the FPGA? So in Catapult, they use PCI Express, which is a pretty conventional way to do it. And they keep getting more new generations of PCI Express, so it keeps going to higher and higher speeds. So it keeps moving. It's pretty high bandwidth. PCI Gen 3 was 8.5 gigabytes per second. Gen 5 is, I think, 4 times that. So it's pretty fast. But it's also pretty high latency. And PCI Express uses physical memory. So that means your program running on a CPU is using virtual memory, which means you don't really know where it is, right? Like you ask for this memory address and a translation layer really figures out where it is in DRAM. Or maybe it's in your cache or whatever. You can't, in order to send data to the FPGA or the FPGA to send it back, some low-level code, like a device driver, basically needs to take all the memory in a process's address space, virtual memory, and copy it into a specific set of physical memory or somehow lock it down. Okay, so usually it's done with a copy. Usually you copy from where you're working on it in virtual memory space to some buffer that's actually been locked down, right? Like I put this here and I know what physical memory it's in and now I can transfer it over PCI Express. It's kind of a pain. The reason it's a pain is because you had an extra copy. Now, if you're doing a lot of processing, that extra copy probably didn't matter much. But if you're not doing that much processing, you're moving lots of data, the extra copy hurts, right? Say you're doing on-the-fly compression, you'd really rather not have an extra copy in the middle of that. So people have looked at alternative ways to connect them. And 2 of the main ones are something called Coherent Accelerator Port Interface from IBM, and CXL, which is now stands for coherent something. Which is started by Intel, but is now an industry standard. So physically, they still go over PCI Express. And we'll talk a little bit later on in the course about what does PCI Express look like, at least at a high level. But PCI Express is like a high-speed serial interface. So they layer on top of that. But they add additional functionality so that now they can use virtual addresses. That's what makes it coherent. So now basically the FPGA or accelerator can ask for data from the CPUs and use virtual addresses. And it doesn't have to be a copy. It's coherent, which means that if the latest copy of that data is actually in the CPU cache, right? So CPU has written some data back, but it's only gone in the cache, hasn't gone back to main memory. CAPI or CXL will actually get it out of the cache, okay? Instead of going to main memory. So that's kind of nicer from the accelerator's point of view. You don't have this extra copy. You can work directly with virtual memory. You can get the latest data from the cache. In theory, it allows more fine-grained cooperation because you get rid of this copying. But in practice, it hasn't seemed to be super important yet. And I think the main reason is there's still a reasonable amount of latency in between these two devices. So fine-grained cooperation may just not be that important. Like if you have really fine-grained cooperation where the CPU is sending a little bit of work to the accelerator, or the accelerator is asking for all sorts of little bits of memory in virtual memory space, then it's just very hard to get an acceleration. So while this makes that better, it may be a use case that just still isn't that common. Whereas if you've got a lot of data that you can transfer over and do a lot of processing, PCI Express works pretty well for that. You did have an extra copy, but that's not too bad. And that seems to be the use case that is more compelling with accelerators right now. Okay, so that's all I had to say about data centers. Any questions on that? Yeah?
Does virtual addresses here, does that mean the operating system maintains the page table for like the FPGA itself?
Yeah, it's a good question. So there's a page table on the CPU. The FPGA, you can decide how big a virtual page table you want to, right? So you basically, to make full use of this on the FPGA, you basically have some virtual memory translation. Does that make sense? So
do the like Linux and Windows, do they support these communication standards?
that's a good question. I mean, CAPI, I think so. Okay, so we have a CAPI machine in a server that we can talk to with an FPGA. And we did that on Linux. So yeah, I think it all works. But we actually found that for us, it also didn't make that much difference. Like we were doing like an acceleration where we could transfer a bunch of data, have the FPGA work on it, and then transfer results back. And if you're doing that, copying things into a certain buffer and then moving, it's not a big deal. So we'll see. The idea of this is maybe you can get some finer grained collaboration, maybe database searches where it's more, you might have smaller transfers, but there's a lot of them happening that this might help. But I haven't so far seen a lot of people show compelling use cases for this. Yeah.
This might be a bit of a weird question, but what's the motivation for Microsoft to release a research paper about the data centers? Like from the industry point of view, if I'm Google and I'm seeing this is how Microsoft scaled their data centers, isn't that kind of like you're giving your competition some kind of like thoughts on how to build data centers?
Yeah, it's a good question.
But I guess it's also proof that you're first to market on this front. Like I wouldn't think you'd necessarily reveal a lot of like the confidential detail. But as opposed to maybe finding a patent on this, which expires after like 200 years, and then maybe you have to maybe even give up intellectual rights to it. I guess if you release a paper, one that's but if you use this to do something and test it on these workflows, and it's the methodology behind it, but then also, we're also the first people to do it, and there isn't a paper on this before, so.
Yeah, I mean, that is always the trade-off publishing in industry. It's part of why industry doesn't publish as much. So you are usually giving your competition information about how you did things. So why did Microsoft do it? I can only speculate. I think part of it is they wanted to partner with the academic community and the FPGA research community. It's hard to do that if you don't tell them that you're doing some of this. So yeah, they get some gains from that, like come work on our problems. Some of the people on the Catawba project, quite senior computer engineering and computer science researchers. And so there's also like a factor that's just personal. They're like, I want to tell people about this. And the company might be like, I'd rather you didn't. But on the other hand, if the person really is like, this is important to their job satisfaction, this is not an easy person to replace, that could be part of the equation too. Because, and I mean, at Altera, that was part of the equation of what we would publish too. I published several papers at Altera, and I can't say that they were necessarily like, they weren't like bad for the company. I wouldn't publish a paper where I said, I think this is the wrong thing to do for the company. But they also arguably were not good for the company. My boss would ask, have you already patented that? And I'd say, sure. It was true, like we had. And it would help you engage with the research community. And it was also important for some of the people who had a strong research background on the teams that they wanted to publish this hardware idea or this software algorithm. The company might be happier to keep it secret, but they also didn't want to like lose those people. And sometimes think of Google, they published a nice paper on the TPU, for example, as well. And I guess part of it, I think, is again the same motivation. They would like people to think about the TPU, use the TPU. They also have some pretty senior people on that if they're not allowed to publish, they might just go away.
I guess another argument is like the idea behind transform being that attention's all you need, and that's a Google.
Yeah.
But I don't think like that doesn't. It's not like that paper results to kind of like direct competition with Google in a sense that this is just like revealing this is how we build our data centers.
I mean, if they kept that secret, like nobody else knew how to build a transformer, that could be a pretty significant competitive advantage for a while, but you probably can't keep it secret forever. So that's probably part of their calculation. And Google, Get and AI has a lot of very strong researchers, and publishing may be part of what that helps them engage with the research community, bring in new researchers. It's part of your advertising, keeping your existing people happy. XAI, right? Elon Musk's AI company, you don't see much publications from them at all. But it's not believed that they actually have much original research. So, I'm not there, but that is definitely the belief within the community. There's just not a lot original there. They're a fast follower, right? So they're taking things that others have done and trying to employ them. I think those two things are harder to separate than, maybe if you're the CEO of the world, you would say, I would like to have the world's best researchers, and I would like them to stay at my company forever and not talk to anyone. But that may not be an achievable thing. And it also may not allow you to bring in the next generation of the best researchers, because nobody knows you have the best researchers because you locked them in the basement, right? So, but you're right, it is a trade-off. So, yeah.
Yeah, just to kind of add to that, also speculating, I think it's like those companies having their researchers published, their research is part of showing their leadership in the space. Like you mentioned the example of Transform, right? And I was reading this article about how Google is always publishing their research, and they have a bunch of Nobel Prize winners, right? So as an upcoming researcher, Google would look like an attractive place to be, so that you go there, you do your research, you get published, and possibly join the ranks of the Nobel Prize winners. So I do think it's part of establishing their leadership in the space, despite the trade-off of selling the secrets, kind of.
Yeah, it makes sense. Cool. Well, let's take a break there for now, and maybe I'll get somebody to prop open the doors. We've kind of hotboxed ourselves, so let's start again at like maybe 11 after. Let's take like a 10-minute break. Okay, go in again. I'm a bit behind. I was a bit ambitious about this lecture, so we'll see how it goes. I'll go a bit fast. Okay, so I'm going to talk about deep learning in FPGAs and a little bit about Blackwell at the end. Okay, so just a few preliminaries. I think most people are familiar with deep learning, so I'm going to give you a few preliminaries. Obviously, deep learning is in everything, right? So you're probably hearing about all large language models. It's in like image classifiers and object detectors and so on. But it's really migrating into a huge number of systems. So here's a couple of examples. So this is an electric car, Chevy Bolt. On average, it takes 6 kilowatts to drive. Like that's the drivetrain in the city. This is NVIDIA's from 2022 card that they recommended for driving assistance. And it took 750 watts. Okay, and that's enough to do some level of driver assistance, but not anything approaching. So what does this mean? Like even like a car battery, this actually has a noticeable impact on the range. Clearly it's not taking as much as the engine, but it's like taking 15% or 12% of what the engine takes, which actually means it's going to hurt your range. So that's a lot of power. So power matters, right? You don't want to just make machine learning inference work. Inference is where you're using the model, not where you're training it. But you would like to minimize its power consumption. You also often have to minimize its latency. Why? In a car, it's pretty obvious. You got data coming from a bunch of video cameras at say 30 frames per second. You want to know you're going to hit a pedestrian like right away. Okay, so you're going to see this on a couple of slides, but one of the techniques you can use to get more throughput from an accelerator is basically batch up data. So for a self-driving car, that would be don't send one video frame to the GPU at a time, send a whole bunch, okay? And that's called batching. And then it'll give you an answer for all of them in rapid succession. And it actually does make the GPU more efficient. It likes to get data in batches. But in a self-driving car, this is not great, because you basically send it 30 frames of video, and a second later it comes back and says the last 27 frames was a pedestrian, but you already hit him, right? So, so a lot of embedded applications like a car, latency matters a lot and power matters a lot. Okay, data centers. Power matters for cost, okay? They can power a lot of data centers, but it's typically about 30% of the cost of a data center is just the cooling solutions and bringing in the power. And it's adding up. It's projected that it'll be 6% of global electricity demand by 2030. That may be too low as AI keeps growing. So this actually has a significant environmental impact. So you'd like to make it more efficient. So in a data center, you care about power as well. You don't have as much the power wall, but you do have, like, I'd like to get more done in the same power budget. A lot of things in a data center, like let's take training. Okay, so there are two things you do with deep learning. You train the model and then use inference where you use the model. Training is latency insensitive, right? You're going to send like millions of training examples through and you want the answer to come back eventually. You don't care like that you get the answer for the first 1,000 faster than the next ones. So training is not latency sensitive. You only care about throughput. Inference in a data center, you might go, well, that doesn't seem like it should be latency sensitive either because I could take all this data from different people and run them all through at once. That's again called batching. It makes the data center more efficient. You can make latency higher, but only to a certain amount because people are impatient. And you might think, well, I can make everybody wait for at least like 100 milliseconds. They don't care about that. The problem is that often like what creates an end user application, like an entire web search or generating a video or something, is actually a cascade of a whole bunch of algorithms. So each of those algorithms has to actually have a much lower latency constraint so that the latency perceived by the end user is much smaller. So in that Microsoft Brainwave paper that I mentioned earlier, their latency constraints are way more aggressive than you would think in a data center. I unfortunately deleted this slide because I had too many slides, but it was really low. Much lower than you would think. And they've been pushing it down. And the reason is because their algorithms are getting more complicated. Their services tend to aggregate a bunch of different components, including multiple machine learning components. They're actually pushing on the latency of each one. Not for training, but for when people are really using it. Does that make sense? Okay. And why am I talking about latency and power? Because those are the things that actually play to an FPGA strengths. Okay. Basically, if you only care about throughput and you're willing to tolerate a lot of batching, like grouping people together, it helps a GPU. So, okay, so let's talk about a few different models. You already saw this picture, CNNs. They process images. They're used to classify them. They're with some extra layers. Okay, so if you add a little bit of extra stuff on the end of this, you can also do object detection. So you not only classify things, you put boxes around them and say person, car, Elon Musk, accelerate. I'm not going to go work at XAI. So that's one of the common workloads. This one is actually less common now. Was common for sequence detection. It's called a recurrent neural network. It's basically, neural networks, their fundamental building block for most neural networks is this multi-layer perceptron. So I have synapses coming in. I take an input, multiply it by a weight. I do that for a whole bunch of synapses, and I get a value at my neuron, and then I basically put it through some activation function, send it on to the next layer. Okay, so that what I just described is a multi-layer perceptron, which is an important component of neural networks. This is also a multi-layer perceptron, so it's at the end of a CNN if you're basically classifying images. And a recurrent neural network basically has feedback connections. And that makes them suitable for sequences. So they're good at processing, doing things like taking sequences of sounds and turning into text, taking sequences of words and turning them into meaning. But these areas have become more dominated by something called a transformer. So I have results on recurrent neural networks. Well, I'm still going to tell you about them. But I'll show you a transformer next. They're not as widely used now because transformers have become dominant for those tasks. Graph neural networks. Okay, so what's a graph neural network? Well, it's a graph. Everybody, I think, knows what a graph is, nodes and edges. And then what you do in a graph neural network is you train, there are a few variations, but basically you train a multi-layer perceptron, like a single multi-layer perceptron, and you're going to use it at every single node, same one, okay? So you've got some features that mean something. What is the weight of this atom? What is its atomic number? Something like that. And then these would indicate connections if this represented a molecule. So this multi-layer perceptron takes your features of your node and you apply it at every single node and it transforms them to new features, right? With weights, just like usual, right? So you're going to do a matrix vector multiply. So you take these inputs, you get your output activations. So far that sounds like, well, that's just a multi-layer perceptron. In a graph neural network, you apply that same one on every single node. Okay, so you've only trained one of these. And then all those nodes that are connected exchange data. Okay, so this node sends data to here, this node sends data to here, and so on. You get data from all your neighbors, you average it somehow. Well, you aggregate it, usually you average it. You update, you basically use that as your new state. You may add that into your current state. And then there's a second layer. The second layer is another perceptron that you trained, one perceptron. And every node now applies that second perceptron on this aggregate state that included the state of the features of its neighbors. And you might do that for, say, 5 layers. You don't do it for a whole lot. And so every layer is a multi-layer perceptron that you apply on every single node. After you apply that one layer, you exchange information with your neighbors to get a new state that's an aggregation of all of your states, and you apply another one. They don't do that many layers, because if you do too many layers, basically you start just averaging the whole graph, and it's too much, like it's too blurry. This is actually a pretty interesting set of models, because by changing the graph, you can adapt, right? So a lot of things can be encoded as a graph, and it turns out that even though I've only trained, say, for a 5-layer network, 5 multi-layer perceptrons, I can actually do interesting things for a whole bunch of different graphs. So this is basically just saying what I said. My final output might be like the final features might represent things about each node, or I might have like one more perceptron that takes all the features that I've computed in the whole graph and computes something. So they use this for all sorts of things, like physics simulation, like figuring out what these proteins or molecules might do, social marketing, so figuring out who's like going to be the best influencer, modeling traffic. So that actually turns out to be useful for all sorts of things. And let's see. Yeah, I guess the key thing to remember here, though, is what am I doing computationally? Mostly matrix vector multiplies, and then some communication and aggregation, which may be a little more irregular. Okay, transformers. So transformers are state of the art for a bunch of things, especially large language models. So these are sequence processing engines. So if I take an input sentence, you're going to use this VPR tool in your 4th assignment. So say it failed. It goes through a tokenizer. So this is like, transformers are more general than large language models, but where they're used the most is for large language models. So I'll use that example. So this gets tokenized, so every word, say, turns into a token. Those tokens each get mapped to a high dimensional vector, so maybe 4,000 or 8,000 dimensional vector, by basically a giant lookup table that's been computed. And then it goes into a transformer. And I'm not going to try to squeeze in how transformers work in one part of one lecture. But basically, there are many, many decoders. And each of these decoders does a sequence of basically matrix multiplications. So each one of these things turns into a vector, many dimensions. It goes into this decoder. The decoder does a sequence of matrix multiplications, something else called self-attention. And then it takes that output and feeds it into the next decoder. And in a big, large language model, there might be like 40 or 80 of these decoders. And then eventually, I get a final vector. That final vector represents my output token, like the next word that I think should be output. In order to generate, so maybe the next word is, two, like TOO. And I feed that back. I go through all the calculations again, and then the next word is bad. Okay, so that the LLM is just trolling you at this point. Maybe it's Grok, right? Like, okay, so what is my point with this? So the dominant computation in this are these matrix vector multiplies that are embedded in here. There are multiple matrix vector multiplies, and then there are a whole bunch of cascaded decoders. And for transformers to work well, they need big vectors. So these are big matrices and big vectors. So a lot of compute. And when we're generating a bunch of output tokens, like all the, maybe you should try changing this command line option to this command line option. This is autoregressive. You can't generate the next output token until you have the previous. You generate one output token, you feed it back, it affects the whole state, and you get the next one. Okay, so it's autoregressive. It's one at a time. We have essentially a loop dependency. So that means that we've got kind of two different kinds of parallelism here. When we're doing our output part, we have less parallelism, right? We have like a loop dependency. And that means that basically we're doing matrix vector calculations. We take that token we just generated, run it through all these matrix multiplications, get an output. When we took this prompt, right, the original text, we actually could generate a bunch of tokens all at once. We could take those vectors and construct them into a matrix. And we could take that whole matrix and run it through here at once if we built our compute hardware or software properly. And now we could actually do matrix-matrix multiplication. So matrix-matrix multiplication is kind of more work, but it's like we're batching things essentially. We're taking a whole bunch of inputs, sending them in all at once. We've exposed more parallelism. It can allow us to get better throughput. So for a transformer, we've got two distinct phases. We've got basically the prompt phase, where we've got quite a lot of parallelism because we can see all the tokens we're going to send in at once and we can make them into a matrix. And then we've got the output phase, or the autoregressive phase, where we only get one at a time. And it's basically more expensive because we can only do matrix vector multiplications. Does that make sense? It's like transformers in like, I don't know, 55 seconds. So, okay. So the common scenarios you're trying to make hardware to accelerate this is, well, either I'm compute limited or I'm memory limited. So if you take a CNN, and you're probably not going to be able, this is just a visualization I'm going to go through super fast. You've got this input activation. We apply these kernels, doing a convolution across it, and we produce an output activation. Don't worry too much about all the dimensions. But the key thing is that the compute's actually a lot more than the data. So for the example I've given here, n is basically the dimensions of my activations, and k is the dimension of my filter, like how big my convolution is. And this is like n to the fourth k squared, which is a lot more compute than the amount of data that I had to bring in. Okay, so I generally am not memory bandwidth limited for CNNs. I have more compute than memory traffic. If we go to most of the other models, so MLPs, LSTMs, graph neural networks, and the autoregressive part, like they generate one token at a time part of a token, they're basically matrix vector multiply. And that is, you bring in the whole matrix. It's a big weight matrix. You multiply it by your activation, like your input or the vector that's moving through, and you get the next stage of vector. And that is basically n squared data, this whole weight matrix, for n squared compute. So generally that's going to be memory limited because it's actually easier to increase compute than it is to increase memory bandwidth. Does that make sense? Okay. So one of the things people do is to try to improve utilization of the hardware, they'll batch. So, and as I stole this from Eric Chung of Microsoft, I think now NVIDIA. NVIDIA's sucking everybody up, but he was at Microsoft when he wrote this. So if you have a small batch size, so you send in, you get one input, like one person's using your transformer, and you send that one input in, your hardware utilization for at least the memory limited parts of this is relatively low because you're waiting for memory all the time. And if you increase the batch size, so instead of sending one person's data through, you wait and you get 1,000 people who are all asking to use your neural model, and you send all of their vectors, their inputs in it as a big matrix, you will get better throughput. You'll move up here, but your latency goes up, right? Because you had to wait for all those inputs to come in. And then even though you're getting better utilization of the hardware, it's not completely linear, right? Like every individual user will see a longer time. It's just you'll be able to service 1,000 of them. So you're going to see in most machine learning results, this is kind of like the Intel versus GPU papers. People should really show results at different batch sizes because GPUs love batching. Okay, so if you're comparing to a GPU, it gets its best hardware utilization out here with big batches, but that's also where your latency starts getting bad. So you kind of have to show the trade-off space to get a full picture. If you're doing batch one, so piece of data comes in, like one user comes in, or I'm going to generate one token, feed it back. I basically, except for CNNs, I'm going to be wind up being dominated by matrix vector multiplications. So order n squared compute and order n squared memory. If I batched up n inputs, so let's say a big transformer, I actually batch up 8,000 people, 8,000 requests, and then I send them through that autoregressive phase. So even though each of them is getting only one new token, there are 8,000 of them that I've sent in at once. I basically could do order n cubed compute now with order n squared memory, because I just bring the weights of a matrix in. I use it to process all 8,000 users through the next step, and then I go on to the next step. Bring another weight matrix in, multiply all 8,000 users, etc. So you can see that my compute went up much faster than my memory if I batched. Does that make sense? Okay, so let me talk quickly about, let's move this back to FPGAs a bit. What are FPGAs good and bad at? So one strength of FPGAs is variable precisions. So if I want to make an n-bit adder, I just use n logic elements. And you'll see exactly how in later parts of the course. But it's probably pretty intuitive. I need like just more bits. I'll use more logic elements. For a multiplier, the way you build a multiplier is basically an array of partial products. So it's actually quadratic. If I want to make a multiplier with n bits, it's basically n squared logic elements. Deep learning is tolerant of low precision, but there's no one answer. Okay, it depends on what exact network model, what layer, how good you want your model to be, etc. So all of these things are actually pretty good for FPGAs. There's no one answer, but you can use pretty small numbers. No one answer is good because it makes it harder to just pre-build everything somebody would want. So that's a strength for FPGAs. You can build whatever numeric format you want. Change the number of bits, and it's not just number of bits, it's also like, how do I use the bits? Is it fixed point? Is it floating point? Is it some kind of mix? You can do all those things. Another strength is what we talked about for spatial, the fact that spatial hardware distributes the data. There's a ton of data and a ton of computation going on in deep learning. And FPGA routing basically you can build hardware where you directly transfer the output of one compute unit to another. And in deep learning, there's a lot of parallelism. You can see where your data is going to go. That works pretty well. This is just motivating why that's important. This is a paper from Mark Horowitz from at 45 nanometers. He took a CPU and he simulated where's the energy going. So 25 picojoules went to getting the instruction out of the cache. 6 picojoules went to getting data out of the register file. So a bunch of power going to control, like figuring out what does this mean and what should I do next, like all that instruction window, etc., that I was talking about before. And then, so that totals up to 70 picojoules. And actually doing the addition that the instruction specified for a 32-bit floating point add was 0.9 picojoules. So about 1% of the energy went to actually doing the computation. Everything else was moving the data and figuring out what the instruction meant. And if you were doing an 8-bit addition, okay, which you could do in machine learning most of the time, it's 0.03 picojoules. Okay, so that's now 1, 2, 3. It's like more than 3 orders of magnitude more energy than the actual computation. So this is kind of the problem that everybody's trying to solve. The compute is actually a small fraction of the energy we're burning. And FPGAs attack that by directly hooking things together, and you don't have to have an instruction stream. Okay, weakness. We talked about program build is expensive, right? So the logic elements in programmable routing, we talked about this last week. If you do it in logic elements, 25 to 30x larger and 3x slower. So that's a pretty big penalty. So you want to use the hardened blocks. If you basically do the multiply, accumulate, and DSPs, et cetera, you're much closer to an ASIC. So from an FPGA architecture point of view, an interesting opportunity is we know we're doing a lot of these repetitive calculations. Can we make these logic elements and these DSP blocks better at those specific calculations? There's a lot of parallelism, and we have lots and lots of DSP blocks, so that's kind of an opportunity. But the DSP blocks in traditional FPGAs were mostly designed for signal processing, like wireless communication, wired communication. Those were the key applications. So there's an opportunity to redesign them for deep learning and be better at the precisions that exist there. Other thing that you can do in FPGAs that can be helpful is you can build anything you want in terms of on-chip memory system. So you have a lot of you have all these block RAMs, you have thousands of them, and basically you can combine them in a huge number of ways. So you can make narrow and deep RAMs, wide and shallow RAMs, you can make multi-ported RAMs and crossbars to them. So you have a lot of bandwidth, and you have a lot of flexibility in how you organize that bandwidth. So that you see some of the FPGA papers, if they can get all of the data on chip, they can use this to get really big wins. Unfortunately, if the network's really large and it won't fit on chip, then you have to go off chip, and everybody uses kind of the same technology to go off chip. So once you go off chip, you start washing out some of this custom memory advantage because you're probably more similar to a GPU. And the way GPUs, their technique for this is batching, right? So they try to build a pretty good memory system, but it has to be just one, and then they try to batch the inputs so that they don't have to go off chip too much. Okay, and the last strength is I/O. So I talked about I/O as like a big value add for FPGAs, is programmable I/O. How does that map to deep learning? It doesn't matter too much well, it can matter some in a data center to have low latency I/Os, but where it matters more is when you're doing inference in the embedded market, you don't know where you're going to do it. So in a data center, it can be helpful to have low latency networking because we could take our model and split it across multiple FPGAs, and FPGAs have pretty low latency interconnect. But the bigger gain is the fact that you can make all sorts of custom I/Os to talk to various sensors and various actuators. So say I'm going to make a smart anti-lock brake. I want to put some machine learning in it. An FPGA may be the only chip that can actually talk to the sensor you need and the actuator you need. And now the challenge is to basically make that FPGA architecture and the machine learning implementation as efficient as possible. But basically, it's not a case where you can just put a GPU in it. It's probably outside your power budget, and it also probably can't talk to what you're doing. So that's where some of the opportunities for FPGAs are, where it's more customized. Okay, so let's just summarize that. If you can use low precision, that's good for FPGAs. High precision is, well, I gave this workshop at Micro. I didn't want to put red on, but it's not good, right? So high precision, so I put yellow. Yellow is as bad as it gets for that. But low precision definitely is more efficient in an FPGA because we can make these small operators. So there also is there's a lot of research that shows that neural networks are tolerant of low precision. There's also research that shows they're tolerant of sparsity, meaning you can remove a lot of weights, like set them to 0. And if you set them to 0, you could actually just skip them. You don't have to multiply by 0 or anything. GPUs actually don't do that well at sparsity because they give it what's called unstructured sparsity. Like just I have zeros in all sorts of random places because it doesn't fit their single instruction multiple thread programming model very well. In an FPGA, because you can build anything you want, you can exploit sparsity of different types by building essentially multiplexer and switching networks and skipping over the 0 weights. If the latency is a tight constraint, that helps an FPGA. If it's loose, then you can batch a lot, and that's going to help a GPU. The network size is not too big, then you can actually fit it on chip, and now you can use the custom memory systems you can build in an FPGA. If it's really big, then off-chip memory becomes more important, and a lot of it's going to come down to how much memory bandwidth did you build, and that partially comes down to how much money are you willing to spend on this, right? Like everybody's using the same technology. Inference is when you're using a model that helps an FPGA because you can use lower precisions. It's usually more latency sensitive. Training helps a GPU, right? Because it needs higher precision and it's not latency sensitive at all. And then if your network is not changing very often, that helps an FPGA because many of the implementations in an FPGA you have to recompile. You have to actually recompile your hardware or redesign your hardware. If your network is changing really often, Google, for example, actually makes updates to their machine learning algorithms that are in not the fundamental style of the network, but they do make updates to the details of the network fairly frequently. One of my colleagues at Google tells me it's like, maybe once a day, maybe once every couple days. That's not a big problem if they're just uploading weights to a TPU, but it is a problem for a style if you basically were actually changing the hardware, right? Because FPGA compiles take a while. So if you're doing frequent updates, I'm going to show you a few different accelerator styles in an FPGA, but for some of them where you actually build like a custom data flow accelerator, it's going to be a problem, right? So it's like parts of this that are green, but parts that are not. So you should take that into consideration if you're deciding what to use. Okay, so let me talk quickly about a few DL accelerator styles on FPGAs. Okay, so this is a chart of efficiency and generality. So some early papers that were accelerating deep learning on FPGAs basically focused on just a part of the network, right? So they might just make the matrix multiplies more efficient or the convolutions more efficient, but they wouldn't target the whole network. They just target a piece of it. And that meant they weren't actually that efficient because they'd tend to get bottlenecked by the rest, the software part that they didn't accelerate, and they weren't that general because they couldn't do the whole network. Okay, so then there was a bunch of work that people did where they made model-specific accelerators. So they'd take something like MobileNet v3 and by hand create an accelerator that did exactly MobileNet v3. So it could be quite efficient, but its generality was not very high, right? If you changed the network, you had to redesign large parts of your hardware. So then more recent work has kind of gone in two directions. One is custom hardware generators. So it can still be very efficient, and it's still basically building a model-specific accelerator. So something that does exactly what this one model needs. So yeah, like ResNet 50 would be, for example, a certain classification algorithm. You might build hardware that only does ResNet 50 for image classification. But instead of building it by hand, you build a domain-specific compiler. So you've built a software program that you send it some class of neural networks. I'm going to show you one where you send it like a CNN, and it basically builds all the hardware for you. Okay? So someone had to code how does this thing work. So somebody built parameterized hardware and a compiler that knows how to hook that together. But once that's done, you can now target different neural models in that class without a lot of manual work. Although you do have to do a recompile through Quartus or Vivado to get your hardware. And then the last style is overlays, right? So they're some kind of soft processor, but a really weird one. Soft processor with some huge functional units to get huge parallelism, a really weird instruction set. You build that overlay, you compile the hardware, and then you can program it through software. And we're not talking about an overlay that looks like a RISC-V. It's going to look very different, and that's how it's going to get performance. But once you've done it, it's quite general, because for a certain class of neural models at least, you can change what it does just with a new instruction stream. Usually that comes with some efficiency hit. Like it still has an instruction stream. This custom hardware generator can actually build hardware that just does exactly what you need. So at least in theory, that should be able to get more peak efficiency. Okay, so two key challenges are always how do we make this easy enough to use, right? Because it's hard to basically say instead of using PyTorch, just go off and design hardware. And how do we make it specific enough to the problem we're solving that we can actually pay for the overhead of reconfigurability, right? That we can get an efficient solution. Okay, so I'm going to give you two quick examples, and they're actually the two papers that you're supposed to read this week. Okay, so the first one is automatically building a data flow accelerator. So it builds basically streaming hardware that only does one thing, and that one thing is make this CNN really fast. Okay, so this work is called heterogeneous pipeline. It basically builds a big pipelined accelerator. So the basic idea is that if we made the other way you can build like an accelerator for CNNs is you build a processing element, some hardware, and you basically map every layer of your CNN. So this basically is doing a 7x7 kernel. This is doing a 5x5. This is doing a 3x3. And they all map to the same processing element. Okay? And to get performance, I'm going to make a bunch of different processing elements and connect them together. So I'll have more than one of these. But basically, my processing element has to be somewhat general. It has to be able to handle all of these different computations, which means more muxing, more control, et cetera. So what HPipe does instead is it basically, it's going to work. If this is my neural network, I did all these convolutions one after the other. So they're feeding each other in my neural model. I'm going to build a different PE for each one of these. And each of those PEs is going to do exactly what I want. It doesn't even know how to do anything else, right? Like that's all it does. It doesn't even need an instruction. So And the way, so it's exploiting essentially a coarse-grained pipeline parallelism. There are many layers, so we're going to have all the layers being processed at once in a pipeline. And each layer is going to get its own PE that is customized for it. And it uses latency-insensitive interfaces between these PEs to make everything kind of work, right? So we have ready and valid signals and back pressure so that basically this is a tractable problem, right? These PEs will always get the right answer even if some of them wind up getting a bit ahead of the others. So that latency-insensitive interface is really useful all over the place. This is what it looks like for, this is actually a certain CNN, MobileNet V1, and it's actually doing object detection. So it's MobileNet V1 plus what's called single shot detection. So the first layers are basically figuring out the big picture in a sense of what am I looking at. And then the later layers are basically drawing boxes around interesting objects and classifying them. And this is where the input comes in. So the input layer comes in here over PCI Express. And all these different colors are different processing elements processing different layers. And so they've all been arranged by Cordis in some complicated structure where the data is flowing through and comes out at the end. Okay, well, it comes back to PCI Express for the final answer. So I guess it shows you the different PEs are of different sizes, and they're all arranged in this complex spatial pipeline. So this turns out to be very efficient, but it requires a new implementation for each model. Right? If I change the model, I got to go rebuild the hardware. So that would be very time-consuming. So part of this project was build a domain-specific compiler. So you input your hardware specifications in one file. So how big is my FPGA? What's in it? And then it takes in a TensorFlow model description, so a graph that describes the neural network you want. And then it goes through a sequence of operations. Kind of sees, can it optimize the graph a bit? And then it basically has to decide how many resources to give to each layer. So it kind of doesn't exceed the FPGA resources, but tries to maximize throughput. And then generates the RTL. That RTL then goes to Cordis, and then you get a bit stream that you can program, and this accelerator does just that one thing. Okay, so this is a visualization of the resource allocation. So basically, it starts off with basically using a minimum number of DSP blocks. I'll show it again. So there's a particular neural network called ResNet50. And it starts with kind of a minimal implementation, and then it looks at like, what it was looking at was the latency to go through each layer. And a pipeline is limited by the slowest stage, right? The slowest layer, because all these layers feed each other. So it basically allocates more and more parallelism, which results in more and more DSPs to the slowest layers until it gets a pretty balanced and pretty fast pipeline. So now all the layers are taking pretty close to the same, having pretty close to the same latency, which means they can all kind of keep up with each other. And I don't think I'm going to go through all the details of this, but basically the compiler is a complicated piece of code. So it essentially has a lot of complexity inside of it of how does it actually hook all this stuff together, how does it generate optimized Verilog, et cetera. But just trust me, it does that. And I guess but it would have probably been impossible to do without using this latency insensitive style, right? So with latency insensitive, where you have like ready and valid signals, you can at least design each of these by themselves and just worry that they've got about the right throughput. The correctness is handled by the protocol. Okay, so, how well does it work? So this is running on an FPGA that's the same process technology as the NVIDIA V100. And basically this is showing the latency we get and the throughput, right? How many inputs we can send per second. So HPipe is up here. So its latency is about a millisecond, and it can do about like over 4,000 inputs per second. If we compare to the GPU, if we give it batch 8, then its latency is worse, about 2 milliseconds, and its throughput is close, but not as high. If we start cranking down the batch size to batch of 1, just give it 1 input at a time, its latency gets better, kind of equals the FPGA on latency, but it's only got about 1/4 of the throughput. So you can see kind of the trade-off on the GPU. And where the FPGA implementation is most compelling is when you need low latency but pretty high throughput. That was on Stratix 10 FPGA. A little while after that work, Intel released an AI-optimized FPGA. So we're going to actually talk about what they did. But basically, they changed the DSP blocks to be better for machine learning. So have more parallelism for small data types. So by leveraging that, the results got better. This is on a different neural network. But basically, now HPipe can do about 30,000 inputs per second, and its latency is really low. Now, this is a network that tends to have lower latency anyway. But compared to a GPU, even giving the GPU a really big batch size of 128, its latency is much worse, and its throughput is still worse. And if we try to go for lower latency on the GPU, its throughput is much worse, like more than an order of magnitude worse, and it still can't get to where the FPGA is. So I guess what I'm trying to show in this is you can get quite efficient solutions for CNNs in FPGAs with this style, custom hardware. And you can get more if you start rethinking the FPGA architecture, which is what Intel did with this one. Yeah?
So this is assuming that your weights could fit in the
Yes, so the weights fit on the chip. We have follow-on work where we put some of them in HBM. So we can put them off chip too, but it's best if they fit on chip. So that's a good point. And CNNs are a good target for this because they're not as memory limited. For most CNNs, you can actually fit the weights on chip. But if you do transformers, for most transformers, you can't. Does that make sense? OK, so that was an example of like a custom hardware data flow accelerator. So let me give you an example of an overlay. And this is something called the neural processing unit that was co-developed with Intel. OK, so this is just an overview of overlays, right? With traditional hardware development and what we just did in the previous design, you take your applications, you implement them in RTL, you run through the CAD tools, and you get bit streams. So it's time consuming for any new application. If you build an overlay, you instead go, OK, what are the kinds of applications that I want to accelerate? You have to work out, well, what kind of hardware could accelerate that with an instruction stream? So you have to actually think of what is my instruction stream and what kind of hardware would that control to get good performance. And now you build two things. You basically build the hardware that has instruction control, so a very customized processor, and you build a software tool chain that can take inputs from the application developers and actually program the instructions for this thing. So it's kind of your development's now broken into two pieces. Make the software tools to program it and make the hardware overlay. Once you've done that, people who actually want to use it are basically just working in software, right? So they have their applications, they write software for your custom overlay, and they go through a fast compile to turn that into binaries, like just machine language instructions, and now they can run on your overlay. So the overlay has a very nice kind of productive flow that looks like once the overlay itself is built, it looks a lot more like a GPU or a CPU. So this neural processing unit it's a very unusual processor. So it's very long instruction word. So it's got 5 stages, 5 very coarse-grained stages. So each instruction word controls all 5 of them. And a single instruction can actually lead to 45,000 operations happening. Part of that's because one of these instruction units is a whole matrix vector unit. Okay? Other pieces of it are essentially SIMD units. And the units are chained together because we know that usually what comes out of the matrix unit needs to be processed with some activation functions. We actually don't go back to the register file all the time. So you do a matrix vector multiply, and then you can feed that into the SIMD units without going back to the register file. So you get performance from all those pieces. OK, so I'm not going to go all through all the details of this, but this is, again, comparing a 14 nanometer FPGA to a 12 nanometer GPU, well, 2 12 nanometer GPUs. This T4 one is the one that's about the same die size or only a little bit bigger than the FPGA. And basically, there's a bunch of different models here. They are multi-layer perceptrons and those RNNs, those sequence models. But basically, it's a bunch faster. It's about 11 times faster than the big GPU and 23 times faster than the GPU that's about the same die size. And that was the compute part. If you add in the time to get data to it from the host, so the actual data transfer time, it's also good. So basically, depending on how much data we're transferring, you get from about 20x to 5.5x performance improvement versus the GPU, like at the system level. So that's because we had a compute advantage, and also it turns out that the communication latency is also lower. Because an FPGA has quite low-level I/O, you can talk to it over low-level Ethernet with low latency. So basically, you get some gains from that too. Okay, this accelerator can also do, it's not in the paper you're reading, but follow-on work made it work for GNNs as well. So I talked about graph neural networks earlier. So this same overlay with a few enhancements can do graph neural networks. These are a bunch of benchmark suites, so I don't want to go through all the details of it. But basically, the green bar is a GPU. The red bar is an FPGA accelerator that basically built custom hardware. And then the two blue bars are this NPU overlay. The light one is when we program it with instructions to try to get a low latency result. And the blue one is when we don't change the hardware, but we just program it with instructions to try to get more throughput. So we essentially are working on multiple inputs at once. So I don't want to get into all the details, but basically, on throughput, it outperforms the GPU by about 2x. Depends on exactly which test case. On latency, it's a much bigger gain, about 60x less latency, because the GPU needs a lot of batching, right? It doesn't do well if you want low latency. And on power, if you want low latency, it's about 900x better. So the GPU does particularly poorly. It's just underutilizing everything. If you need low latency, you do low batching. And that's kind of all the things I wanted to say about that. So I guess the summary is there are just two different ways that I've shown you here where FPGAs can get good deep learning inference performance. You can automatically generate custom hardware, but I think you have to automate it. You can't do it by hand. Or you can make a software programmable overlay, but it's got to have an architecture that's pretty customized to the class of neural networks you want. And I think I'm going to change. Yeah, I don't think I'm going to go through the rest of that. The rest of that we'll talk about later. OK, so if people want to, I can go through Blackwell in the last like 4 or 5 minutes, or we can just end it here. What would you prefer? OK, so I'll show you a bit about Blackwell. I didn't make that many slides, but if you want to ask me questions about it, as you can tell, I'm not at NVIDIA, but I have actually been studying this a little bit because I do spend part of my time at Cerebras, so I looked at this as an interesting thing I should know about. OK, OK, so NVIDIA Blackwell is their latest production GPU. And at this point, like NVIDIA's market is much more machine learning than it is graphics. Graphics is still significant, but it's like, AI is like the tail that wags the dog. OK, so Blackwell is first and foremost optimized for transformers, okay, and particularly large language model transformers. It's a huge market, so think of it as a programmable ASIC. Okay, so what have they done? More silicon. So Moore's law has slowed down. So part of, and basically getting more performance on these models has a lot of economic value. The models keep getting bigger. So what did NVIDIA do? There's a reticle limit of how big a die you can build. It's basically how big the optical lithography cameras can expose. So they're basically at that reticle limit, which is about 815 millimeters squared. So this is basically the biggest chip you can fabricate. And they don't have one, they have two. Okay, so that's one chip there, that's another chip there. They take that whole thing, they put it on what's called a silicon interposer. So a silicon interposer means it's silicon again. It's at a less advanced process technology, and it only has wires. Okay, there's a bunch of different variations of interposers, but this is the most common way to do it, and it's what they use. So underneath this, if I etched away the silicon, is more silicon. It's a different die. And the value is I can make pretty small wires on it, and I can make small micro bumps. And that allows me to have a much higher density of interconnect wires between these dice than I would get if I just put them both on a circuit board. So the whole thing has 208 billion transistors. It's in a 4NP process. What does that mean? It's not clear, right? The numbers keep getting smaller. Nobody knows what the numbers mean anymore, except small is better. But it is a very advanced process, and the N stands, I believe, for NVIDIA. So it's actually customized for them by TSMC. 1,200 watt power budget. So this is, You're right, actually, this is your microwave. So the way, so if you can harness it, the waste heat from this could actually cook your food pretty quickly. So the nice thing about these silicon interposers, so it gives you a bigger system, and because you can get so many wires, and they're pretty short, right? So that means you can clock them pretty fast. They get 10 terabytes per second of bandwidth between them. So they behave, not quite, but close to like one chip, right? That's what an interposer gives you. We'll talk more about interposers in the FPGA context later in the course, where I can give you some very detailed data. I can't really give you any more data than what NVIDIA has published, but they get a lot of bandwidth between them. So they act like a single huge GPU. Okay, that's not their only use of interposers. So you see these 8 things here. Each of those is a stack of high bandwidth memory. High bandwidth memory is a 3D stack of DRAM chips. So I believe these ones are 12 high, so 12 chips stacked on top of each other. And you do that 8 times. So you actually have a lot of DRAM chips. And the way you connect to them, because each of these HBM devices has a 1,000-bit bus to the GPU, so you connect those with silicon interposers as well, okay? So that you get, again, relatively short wires, and a lot of them, you can clock them fast, and you get these wide interfaces. So for their B200 devices, they now have a B300 as well, but which is even a little bit higher end. It's similar, but the specs are slightly better. They get 192 gigabytes of total memory, and they get 8 terabytes per second of total bandwidth. So it's huge memory bandwidth and actually a lot of capacity. So this is very expensive. I've seen teardown analyses of this by a company. Not actually one that I work for, but just, it's okay. So let's just say I've seen data that is not from NVIDIA that estimates that the HBM is more expensive than the GPU. Okay, so this is not cheap to have that much memory, and HBM is a more expensive type of memory. So this is actually interesting. NVIDIA just released something called the Blackwell CPX. The Blackwell CPX is, the same, well, it's basically one die. So they don't do 2 die, they do 1 big die. So it has less compute performance because of that. But the bigger change is they don't have HBM. So they get rid of the HBM, and they instead have a wide bus to graphics DDR, which is probably the best you can do if you don't use HBM, but it's a lot lower bandwidth. So why did they do that? It's because the HBM is really expensive. So this CPX device, I showed you in a transformer, there's kind of 2 phases, right? When you're doing the prompt phase, you send in, okay, let's say you send in a homework problem. I know none of you would ever do this, but you take the whole homework problem, you send it in. Okay, so that whole document is a whole bunch of tokens that could be put in, they're turned each into a vector, put into a matrix, and they can be sent through as a whole batch. So you get matrix, matrix, multiply, which means you can bring each weight matrix in, there are a lot in a big transformer, process all of those tokens, and then bring the next weight matrix in. Okay, so it doesn't need as much memory bandwidth. So for the prompt phase, we don't need as much memory bandwidth, so they actually released a device that is optimized not just for transformers, but for the prompt phase of transformers. So the idea is if you're building a data center, you buy half CPX devices, you use those for all the prompt, like the homework document came in, and then you actually transfer the intermediate state data to some of these B200 devices, which actually have the HBM, and they produce the solution 1 token at a time. Okay, so it's pretty interesting. It does show you how important, like how this is kind of complex. Well, I guess a couple interesting things: how many dimensions there are you're optimizing, and also how big a market this is, where NVIDIA can actually optimize not just for transformers, but for even specific pieces of the transformer inference. Yeah.
When you say very expensive, is that money? Is that power? Is that?
It's money. Yeah, so HBM is an expensive technology. Its power consumption I'm not sure about. It probably still dwarfed by this GPU.
Gotcha.
It won't be negligible, but the GPUs are pretty power hungry. So, okay, so if you look inside that thing, what do you see? Well, so it's still streaming multiprocessors. So I told you that a streaming multiprocessor is like the core in a CPU. And if we look at this is a bit small, but I'll post the slides. It's pretty similar to what I showed you in an earlier generation NVIDIA GPU. So we have 4 sub-pieces Each of them does 32-way SMIT, so like SIMD. So it basically has 128-way SIMD with a bit of extra flexibility. That's the CUDA cores. Notice in this diagram, they made the tensor cores bigger. Okay, I don't know if that actually reflects silicon, but it reflects what their focus is for machine learning. So, so they've got 4 of these tensor cores inside of their streaming multiprocessor as well. And the tensor cores are small matrix multiply units. So why do they do that? So basically they're streaming hardware. So this is actually where you can see these compute models, I think, are an interesting way to think about things. The primary organization is SIMT or SIMD, but they bolted on streaming hardware to accelerate a key computation, which is matrix multiply. They can't do huge matrices. They do essentially small matrices at a time. But the way I showed you, you can tile a matrix. You can use that same technique to basically compute sub-matrices using these tensor cores and keep adding them up and do really big matrices. So why do they do that? Well, n is not huge, but maybe it's like 8 by 8 by 8. You have order n cubed compute for order n squared data. Basically, if they build enough compute here, and they have built enough compute, even their register file ports are not enough. Like they can't feed it from even their first level of memory. But if they basically reuse the data by doing an entire submatrix, now they can feed it. Because they just have to feed it, for example, 64 numbers for each of 2 matrices, and they can do 8 times 8 times 8, which is like something like 4,000 operations. So they get a lot of data reuse. So it avoids them being limited by their register memory bandwidth, which is very expensive to expand. Like if they want to do 8 times as much register memory bandwidth, that's a very expensive thing to do. So this is much more efficient. What feeds these they actually are not fed by the register files because they don't need as much bandwidth now. So they're fed by the shared memory. So there's this shared memory, which is like the L1 cache, but you usually explicitly manage it. And a new memory. They have this tensor memory. So they have 256K of shared memory, and that can feed into one of the input matrices of these. The other one comes from this 64 kilobytes of tensor memory. And that's where the partial results go back to, because we kind of do a block of this, and we need to keep our partial results and keep adding to them to do the whole matrix. The CUDA cores are not that different. So still SIMT, still 128-way kind of parallelism within a streaming multiprocessor. Okay, so these chips keep getting bigger, right? This is like actually 2 chips now that they're calling a GPU. And physics doesn't allow you to communicate over really long distances very quickly. So their hierarchy is getting deeper. So their lowest level hierarchy is a CUDA core, which is like a SIMT lane, right? It's really kind of like a functional unit. Then they have the streaming multiprocessor that we just talked about that has 128 of these CUDA cores or lanes and 4 tensor cores or matrix multiply accelerators. And now they've grouped the streaming multiprocessors into this GPC, which I think stands for General Processing Cluster. So they group about 20 of them into a General Processing Cluster. This is a die photo. You can see they have, this is actually a slightly different version of Blackwell, it's the 202. But they've basically got 12 of these processing clusters across the die. And each of them has about 20 streaming multiprocessors in them. So, and this is visible in their programming model. So why'd they do this? Because it gets hard. It's slow to communicate from one streaming multiprocessor to this one over here. It's going to have to go through a multi-level switch network. So basically, they've added another level hierarchy. You can ask for your threads, your compute, to be co-located in one GPC, and your communication between those streaming multiprocessors is more local and it's faster. Okay, so you can't hide spatial effects. Like you can't hide physics. So what NVIDIA is doing is they're kind of adding more hierarchy to give you some of the spatial effects. Their delays even within, so I don't know about this GPU, but I know in their previous generation GPUs, their delays between streaming multiprocessors were not uniform because some of them are physically closer to each other. And I know that at least Microsoft will actually profile that in their kernels to try to figure out which ones are close to each other and try to optimize for it. So even in like programming models where it's not immediately apparent who's close to whom, power users try to figure it out to try to get more performance. So kind of spatial effects are there no matter what. Okay, another big thing they're doing is precisions. This has been going on for a long time. So they They can do FP32. I didn't even put it on here though, because their primary thing for machine learning is FP16, FP8, and FP4. FP4 is new. They didn't have that in any of their previous GPUs. So what happens when you make smaller data types is the compute units shrink. So we already talked about that some, and we'll talk about it more for FPGAs. Also, the on-chip memories can keep more low precision units fed, right? So, and this is the thing that usually defines how many units they'll allow to be used at once. So basically, if you do compute in FP4, you will get twice the throughput of FP8 and 4 times the throughput of FP16. And that's basically the rule that you can follow for almost all their GPUs. It's like it's like by data path width, right? Which means that their primary limiting factor is how much can the on-chip memories feed, right? So what do they use this for? FP16 is at this point stable for both training and inference. You normally do not have to train in FP32 anymore with good training recipes. FP8 is good for inference if you're careful, and some training, although it's harder, so it's a bit more risky for training, but some people have shown it can work. FP4 is okay for parts of inference, so you usually don't take all the layers or all the decoders in a transformer, but you can take some of them, and maybe parts of training. So NVIDIA has papers where they say they can actually take some of the layers in a transformer, or some of the decoders, and actually move them to FP4 and with some tricks still train them. But it's a bit more dodgy. So anyway, all these things get used. This one is the newest. Probably the jury's the most out on how much can you use it, but it's believed you can use it at least some. And then the last thing is network bandwidth. Okay, so they have PCI Express to talk to the CPU. But on top of that, NVIDIA has built NVLink, and they didn't build this just for Blackwell. They've had this for a while. But it's a high-speed interconnect that is high bandwidth. So one GPU has 18 50 gigabits per second lanes, okay? So that translates to 900 gigabytes per second each way. Actually, this might be, I probably should have had a B here, but you get the idea. So they've got a lot of bandwidth, okay? We're going to talk about serial interfaces a little bit later, but this is a high-speed serial interface, so it's got a lot of bandwidth. And they can basically use this to connect 72 GPUs together. And those 72 GPUs in their programming model, NVLink is coherent, okay? So that means, what it means by coherent is they can actually use a global address space. So it makes it easier to program. You can actually say, here's my address, and it could map to any one of these 72 GPUs, and the hardware will go get the data from the right thing. It'll be slower, but it makes it easier to scale up, where you take this huge LLM, and you might put different layers on different GPUs in a pipeline, or you split a certain layer or something. So anyway, and they keep making NVLink faster. So this number of GPUs that they can connect efficiently keeps going up. That's all I had to say about Blackwell. It's a pretty interesting piece of engineering. Okay, sorry for going over time. Thanks.